All-powerful God, you are present in the whole universe and in the smallest of your creatures. You embrace with your tenderness all that exists. Pour out upon us the power of your love, that we may protect life and beauty. Fill us with peace, that we may live as brothers and sisters, harming no one. O God of the poor, help us to rescue the abandoned and forgotten of this earth, so precious in your eyes. Bring healing to our lives, that we may protect the world and not prey on it. That we may sow beauty, not pollution and destruction. Touch the hearts of those who look only for gain at the expense of the poor in the earth. Teach us to discover the worth of each thing, to be filled with awe and contemplation, to recognize that we are profoundly united with every creature as we journey towards your infinite light. We thank you for being with us each day. Encourage us, we pray, in our struggle for justice, love, and peace. Our Lasallian prayer. I will continue, O my God, to do all my actions for the love of you. Saint John Baptist de La Salle, pray for us. Live Jesus in our hearts forever. Amen.
Hi everyone, and welcome to the last session of TAAS 3, the metabolomics approach and its different applications. Once again, I am Chris Argamino of the DLSU CIF, and I will be your host for today. So finally, we are down to the last session of the webinar series. So you may be wondering why this was held on a Friday, unlike the past two sessions. But unfortunately, our guest speaker is only available on weekdays, and this is the closest one to a Saturday. So, don't worry, don't fret. We assure you that spending a couple of hours with us on a weekday will be worth your time. So, as usual, roll call muna tayo. Can you type in the chat box or comment section for Facebook your location so we'll know where you are right now? So, antay tayo ng mga answers nyo, ah. So, we have one from Baguio, Bataan, cool, and Palawan, Cavite, Pasay, Malabon, Makati, yan. Iligan, wow. Okay. Bukidnon, Tacloban, Baños, Baguio. So let me check din sa sa ating Facebook live stream if anyone has responded. So we have one from Davao. Okay. So thank you so much for answering. Ayan. Our meeting question. So to those of you who are all over the Philippines, magandang umaga, mayong buntag sa inyong lahat. Thank you in advance for attending this webinar, and we hope that you learn a lot from our culminating session today. So another question, ayan, so ready lang tayo dun sa raise hand. Ayan, raise hand tayo dun sa Zoom natin kung mahilig tayo sa stat o math. Mga natin. So check natin yung participants natin. Are you, tawag dito, fond of math and statistics? Meron ba kayong raise hand function? Ayan. Sa inyong mga Zoom ngayon, active ba? So, may mga naman. May mga nag-respond, may dalawa. Ayan. So again, the question is, are you fond or mahilig ba kayo sa math or statistics? So yun yung topic natin for today. Ayan. So may mga ilan-ilan. So actually, medyo ina-expect ko na kasi hindi talaga ganoon karami. Most likely. For sure, hindi natin siya naiiwasan dun sa mga competitions natin sa lab. Medyo no choice. I know a lot of our chemists and those who are also in other scientific disciplines are not that fond of numbers. But yun nga, hopefully, will have a fresher perspective on the topic later, especially after learning how useful these tools are for our research activities and especially in the field of metabolomics. Okay? So before we officially begin the event, may I remind everyone again of the general privacy notice and house rules for the entire webinar session today. So we've already seen this earlier before the start of our session. This was flashed. So first, recap lang natin. Screenshots and video recordings of the event will be done and may be used for print, online, and social media publications. So if you have followed our Facebook page in the past few weeks, we are posting screenshots of our Zoom fee after the event. Second, this event may include media coverage and story releases online in print or on traditional broadcast channels. Third, information collected via registration or media capture may be kept for archival purposes in the Google Drive account of the CIF team. Fourth, personal recording of the session shall not be done to respect the rights of the participants in the session. The recording of the session shall not be reshared and or reposted online without prior notice from the organizer to prevent unauthorized disclosure and processing of personal data. Sixth, discussions and conversations of a personal nature not related to the ongoing session shall be discouraged to prevent unintentional and or unauthorized disclosure of personal data. Now for the house rules. So first, this webinar is being recorded. So you see see that on your screen. And you will be able to view it on demand later via the live section of our Facebook page. So later, to guide you, we'll be posting the link to the past events or past webinars we've recorded and uploaded automatically doon sa ating DLSU Central Instrumentation Facility Facebook page. So if you haven't liked our page yet, please do so. Ayan. Number two, at any point in the webinar, feel free to type in your questions via the Q&A box for Zoom and via the chat box for the Facebook live stream participants. Number three, the speakers will try to address as many questions as possible during the open forum. If time does not permit, our team will get back to you with the answers via email. Lastly, e-certificates can be requested by participants who have fulfilled two requirements. First, you must have pre-registered to the webinar using the Google form we've posted in our page. And second, you must submit the webinar evaluation form that we will be posting later, yung link dun sa ating Zoom page at sa Facebook. So remember that the webinar evaluation form can be submitted until 11:59 p.m. tonight. Okay? So quick recap tayo, last March 13, we had the second session of the third installation of TAAS. In that session, we were lucky to again have Dr. Lacerna and Dr. Mel Garcia of the DLSU or LaSalle Food and Water Institute. From Doc Karen, we learned her experience about the metabolomics workflow, including a couple of details, medyo marami actually. She talked about experimental design, sample collection, common analytical platforms used in metabolomics. Aside from those, there was also an in-depth look at mass spec instrumentation. So hopefully, we all learned a lot from that discussion. If not, or if you want to go back to that, again, these are all available in the live tab of the Facebook live stream. Of the Facebook page of DLSUCIF. So from Dr. Mel naman, Dr. Garcia, we were made aware on the issues on civet coffee and also the process of obtaining them and their coffee surface morphology via SEM and EPX. Pero again, for me, the most important takeaway from that talk was the realization of the importance of systems analysis. So yung consideration natin ng impact ng actions natin sa lab or sa research doon sa mga stakeholders natin, those who will be benefiting from the results of our experiments. So now we are on to the last session of the third installation of TAAS, and we're glad to have Dr. Lacerna back. So as our keynote speaker, she was able to present in all two sessions before. So now she'll be culminating her talk with chemometrics in metabolomics. And for our guest speaker today, we're very lucky to have the Vice Chair and an associate professor of the DLSU Chemistry Department, Dr. Rodolfo Sumayaw Jr. or Sir Rod, for the application of metabolomics for clinical studies naman. Okay? So very well-rounded tayo. We started with plant metabolomics and then food, tapos ngayon naman clinical, yung ating application for metabolomics. So clearly, metabolomics really has a lot of uses or a lot of applications. So first, before heading to the heart of the webinar proper, let me introduce you to the team behind the CIF. So first, we have Dr. Drexel Camacho, our director, of course. You've seen him already if you've attended the past events. Next, we have Dr. Romeric Pobre, who manages the IEM lab or the Integrated Electron Microscopy Lab. Next, we have Dr. Marie de los Reyes of the Imaging and Cell Culture Laboratory. We have another one, which is from the Wind Tunnel Testing Laboratory. We have Dr. Lawrence Ganlim. And then reporting to the laboratory managers, we have Dr. Virgilio Ebajo Jr. of the NMR Lab. We also have Dr. Jose Esmeria Jr. of the Integrated Electron Microscopy Lab. And then you have me, yours truly, for the spectroscopy lab and on an interim basis, yung chromatography lab din. We also have our lab analysts who report to us and help us in the daily activities. We have Jude Roland de la Cruz of the NMR lab, Alona Intac of the spectroscopy lab, and Dean Hazel Pelobello of the chromatography lab. All of us are supported by our office assistant, Ms. Jessica Marie or Jeka Monterde. Okay? So, yun. So, on to the next session. We were meant to show this since the first session, but unfortunately, we stumbled across some technical difficulties. Here it is finally, the CIF promotional video. Let us watch the video to introduce you to our humble facility.
The De La Salle University Central Instrumentation Facility is the university's premier instrumentation facility located at DLSU Laguna campus in Binyan City, Laguna. Under the umbrella of the Office of the Vice Chancellor for Research and Innovation, it aims to elevate the quality of scientific research not only in the university but of the entire country. Allow us to give you a tour and have a closer look at our facility.
The Nuclear Magnetic Resonance Laboratory operates a high-resolution GL600 MHz NMR spectrometer. With a 14 Tesla superconducting magnet, this is the most powerful NMR spectrometer in the Philippines. We can perform analysis for both liquid and solid samples. We offer NMR analytical services to all clients, and we also offer workshops and trainings on NMR principles and hands-on operation.
The spectroscopy laboratory handles UVVs with reflectance with a capacity of up to 900 nanometers without attachment and up to 1400 nanometers with the ISR 2600 attachment. We also have FTIR with ATR for quick analysis of liquid and solid samples. Particle size and zeta potential analyzer, a non-destructive light scattering technology to measure molecular weight, concentration, and zeta potential of particles ranging in size from 0.3 nanometers to 10,000 nanometers. ICP-MS for simultaneous trace level analysis of multiple elements, particularly in metals. And Elemental Analyzer for simultaneous analysis for carbon, nitrogen, hydrogen, sulfur, oxygen, or for the combination of CNS, CHN, CN, O, and Cl in one simple run.
In the chromatography laboratory, we have the QTOF LCMS, which can perform sub-1 ppm mass accuracy and can reach up to 5 orders of in-spectrum dynamic range, which improves detection of trace-level targets in the presence of high-abundance compounds. Analytical HPLC, with detectors UV, refractive index, and gel permeation or size exclusion. Preparative HPLC, with fraction collector, which has a fully automated sample injection and the capacity of 132 samples to increase the dynamic flow range up to 50 ml per minute at maximum 420 bar. And lastly, the GCMS with headspace autosampler with a mass range up to 20,000 mass per charge ratio.
The Integrated Electron Microscopy Laboratory serves the morphological and compositional imaging needs at the micro and nano levels. We have the Field Emission Scanning Electron Microscope with Energy Dispersive Spectrometer, Transmission Electron Microscope, and Focused Ion Beam. The Imaging and Cell Culture Lab handles confocal scanning laser microscope with live cell imaging. It is also equipped with cell culture laboratories for mammalian, plant, and bacterial cells.
We also have the wind tunnel testing laboratory with the Eiffel-type wind tunnel equipment, which is used to simulate airflow measurements, typhoons, airflows in urban buildings, aeronautic and aerodynamic studies. It is located at the Richard Lee Engineering and Technology Block.
The sample preparation laboratories are available for processing samples equipped rotary evaporators, freeze dryer, sonicator bath, sonicator probe, ultra pure water purification system, pH meter, balances, ovens, and standard glasswares. To serve the research needs of DLSU students, CIF offers the Graduate Research Residency Program where the students can use any of the available instruments for their research needs. The program was able to graduate 2 MS students on time, and we are looking forward for more graduate students. The recent program, Tuklas Lunas Fellowship Program, in partnership with the OSU PCHRD, produced 15 research fellows capable of molecular level conduct of natural products research relevant to the nation's goal in search for cure for some diseases. The CIF also conducts the Balik Scientist hosting, wherein we invite Filipino international experts through the Balik Scientist program of DOST. With this, we were able to share their knowledge and expertise through webinars, workshops, and consultations. Partner with us for your research needs. For more information, contact us.
Yun. Thank you, Hazel, Jude, Jeka, and Alona, our lab colleagues who work together on the video. So they're also the ones behind the scenes in organizing this webinar and the past webinars we've had. So question, were you enticed about the laboratories that the CIF has to offer? So raise hand tayo guys kung medyo na-entice kayo. Kahit medyo lang. Yan. Kaya ba yun? So we see a few hands. 6. May heart pa nga na isa. Thank you so much. Ayan. So actually, tawag dito, hindi nyo kailangan actually mag-sana all para magka-access sa mga ganitong gamit since we're actually open to accepting samples from anyone who is interested. Not only in the Philippines. In fact, we've had recently a client na galing US naman. So if you're open to collaboration for a funded project, also let us know. Or kung hindi man collaboration, okay lang, send nyo lang kami ng message or email nyo lang kami if you want your samples to be analyzed here at the CIF. Sana nainganyo kayo for dun sa facilities natin, and we hope to collaborate with all of you in the future. So again, for inquiries, you may send a message via our Facebook page, DLSU Central Instrumentation Facility, or you may send us an email via cif@dlsu.edu.ph. So balik tayo dun sa program. We will now be reintroducing again our keynote speaker. Our keynote speaker is a Department of Science and Technology, Philippine Council for Health Research and Development Balik Scientist awardee. She earned her BS in Chemistry from UPLB, University of the Philippines, Los Baños, and spent her early professional career in a testing lab in the academic setting and a pharmaceutical company in the quality assurance section, also here in the Philippines. So she then spent the next decade in the National University of Singapore as a PhD in chemistry student, research assistant, and as a postdoctoral research fellow, covering a number of projects. Medyo marami to actually. If you've been to the past webinars, you've seen her work, involving various applications of metabolomics and analytical science in areas such as preclinical/clinical, agricultural, food, forensic science, and environmental research. So the Santa Rosa Laguna native, a rising research scientist in the field of metabolomics, has published more than 10 papers on the topic covering various applications. So everyone, again, we are honored to introduce you to our keynote speaker, Dr. Ana Karen Lacerda.
Okay, thank you very much, Chris, for the kind introductions. Okay, good morning, everyone. So we are on our last leg or in our final installment of this webinar series on the metabolomics approach and its different applications. So I hope you had been able to learn a lot from the first two sessions, and hopefully in this last session you will also get to do so. Okay, so in the past sessions, so for in the first session, we have covered the introduction to metabolomics and its applications. So we have answered the what, why, when, and where of metabolomics. We have also covered the hows of metabolomics in the second session last 13th of March. And from there, you were able to know some parts of the metabolomics workflow up to the data acquisition. And so for today, we will cover more on the chemometrics in metabolomics and beyond. So for this particular session, we'll cover more of like the data analysis as well as the what are the subsequent steps of the metabolomics workflow. So again, our title is chemometrics in metabolomics and beyond. So as mentioned, our coverage will be chemometrics plus the rest of the metabolomics workflow. Okay, so we have covered more of the definition of the problem, the experimental design, sample preparation, and data acquisition in the previous session. Today, we'll cover more of the second half from the data processing up to the validation part. So, from the data acquisition, we go to data processing. So in we know, right, in chemical analysis, sample preparation is very important. Um, uh, it is known that a lot of the analytical variation comes from the part of the sample preparation. And so it is very important that we optimize the sample preparation in order to get accurate and meaningful data. The same goes for for data analysis or or the chemometric analysis. We need to do um, uh, proper and appropriate data pre-processing before we subject it to subsequent data analysis, or in this case, in our case, we will be using chemometric analysis. And here, this is where like peak alignment, things like peak alignment, data binning, baseline correction, noise removal, smoothing. If you have some fluctuations in your signals, you have to make use of like smoothing algorithms to smooth that out. You can also have your variable selection to ensure that you get your the variables that are related to your samples rather than your background or contaminant signals. You also can do like some initial outlier detection, but you can also have this outlier detection part during the chemometric analysis part as well. But if you already know that there are some samples that are outright can be rejected in the pre-processing step, then you can also do so. Okay, so we'll talk about data pre-processing. So NMR-based metabolomics and MS-based metabolomics will have different pre-processing steps. And so now we'll cover first more of the NMR data pre-processing. So, usually there will be like some chemical shift variations in your NMR spectra, and this can be due to a number of things. It can be due to changes in pH, it can be due to differences in concentration, it can be because of protein interactions. And usually, you have to perform an initial chemical shift calibration. And this is done using an internal standard. So, for example, your internal standard will have a peak at the 0 ppm, so you can adjust the chemical shift of that particular compound to the 0 ppm, and that will help align or help calibrate the rest of your spectra. You can also make use of known signals. So there are compounds that we know has a specific peak at a particular chemical shift, and so you can use that for the calibration. For example, glucose has a peak at 5.23 ppm, so you can calibrate your spectrum at that particular chemical shift. Um, you also um, so these internal standards that is commonly used include your tetramethylsilane for example, for deuterated chloroform. You also have trimethylsilylpropionic acid and DSS for deuterium oxide. You also have this one is a bit more new, but its advantage over TSP and DSS it has less interactions with proteins, because TSP and DSS can have some interactions with proteins. They can also have a bit of chemical shift variations because of pH, but more so for TSP. Um, so this DSA is actually another internal standard that you can use. However, yun nga, the disadvantage is hindi siya readily available. So still, most people will use DSS in D2O for NMR metabolomic experiments. You also can do spectral alignment. So a lot of the NMR processing softwares will have some functionalities for spectral alignment. So you can have global alignment. That means using the particular algorithm involved, uh, the whole spectra is adjusted. If you're comparing like several spectra, so all of them will be aligned in terms of like the chemical shift. In some cases, even though if you perform global alignment, there might still be like regions of the spectra that is not yet well aligned, and so you can still further do local alignment. Pero selected lang yung mga softwares that can do this, and I think one of them will be your Mestranova. So MNova NMR has this functionality for local alignment of certain peak clusters. If there are pH-related shifts in Kinomix, like one of the processing softwares that we use, having pH indicators like imidazole, formic acid, creatinine can help you adjust as well the chemical shift of some metabolites that are commonly affected by changes in pH, and therefore it will be easier for you to identify them. In some cases, or in order to also avoid these types of pH related shifts, you can actually just use a buffer solution to control the pH of your samples, and so this will help prevent these pH related shifts. Okay, so In addition to that, there are other pre-processing steps. So common pre-processing steps in NMR will be, of course, your phase correction and baseline correction. Aside from that, in cases wherein there are some protein interaction effects, you might need wherein there is some line broadening, so you might have to do some line width adjustment. And you can delete certain regions that are associated more with these different like your solvent peaks, your water, so your HOD peak. So you would want to delete that as well as your urea peak in urine samples, and in order to also prevent the radiation damping. So para mas ma-highlight mo yung signals, there are also some pulse sequences that can allow you to suppress some of these peaks. But if not, if you were not able to do it, you can do region deletion before you proceed on with the rest of your data analysis. Okay, so softwares for NMR data preprocessing, of course, though there are those that are more based um on the instrument that is used. So top spin will be for Brooker. I think you can also use it for the analysis of um the other data formats that are from other vendor or other manufacturer. Um, you also have your OpenV NMRJ. This is mainly suited or uh, mainly used for um, spectra or NMR data file that has been obtained uh, from the VNMRJ platform of Agilent or Varian NMR. So Agilent has already discontinued their NMR business. So the software that is used for data acquisition, which is VNMRJ, has been converted into an open source software. So this is your Open VNMRJ. um, and as mentioned, you have your Mest Renova suite of processing softwares, and they have specifically their own suite for NMR processing. You also have ACD Lab, so they have their spectrus for the analysis of pre-processing and processing of your um, MS, NMR, IR, other spectroscopy data. Lastly, is Kinomics. So Kinomics is actually um, specific for NMR. It has functionalities that allows you to process as well as to profile. So later on, I will show you like how you make use of Kinomics for profiling. So it allows you to perform quantitation on the data that you acquired. And it has capabilities for you to build your own library. So you'll be able to add on um, compounds that are from your own analysis that may not be present in any databases by making use of your compound builder, and subsequently you can build your libraries using the library manager. So this one is actually a very useful tool for metabolomics. So this will allow you for targeted or quantitative profiling of your NMR spectra. And I think this is not exhaustive. There are some softwares that you can also look into in terms of like mixtures analysis. So I think Brooker has the Amix, or the analysis of mixture. The abbreviation is Amix for um and Geol will also have their own softwares. I apologize. I haven't really used the NMR yet in CIF, so they will also have its own set of softwares. Um, Okay, so that is for the NMR data processing. Usually in NMR, data is either binned or profiled. So when we talk about binning, the whole spectra is divided into bins. So you can divide bins of either zero point zero 0.04 or smaller zero point zero 0.02 ppm, and then you get the area for each bin. So the total area within each bin will be the one that is used for the analysis. And this allows you to compensate for minor changes in line width and chemical shift. So I've mentioned earlier, certain in certain cases you can have protein interactions that can affect your line width. You can also have pH changes that can also affect your chemical shifts and so forth. And so this spectral binning can compensate for a bit of these effects. And you can also do relative concentration based on the total area. So you can obtain relative concentration information based on the total area, and internal standard is not required. So you don't perform absolute quantitation. So you can just do relative quantitation based on total peak area. And so, yun, hindi kailangan yung internal standard. On the other hand, meron tayong mas quantitative approach, which is profiling. And it makes use of signature NMR profile for each compound for identification and quantification. So so we know that in NMR, for example, your glucose, your creatinine, they will have specific signals at specific chemical shifts of specific multiplicity. So for example, you will have a singlet at 5.23 ppm for glucose. But aside from that 5.23 peak, glucose will have a whole cluster of peaks in the 2 to 3 or even 4 ppm region. So they have these characteristic peaks or peak clusters, and these can be used to profile and quantitate um, your uh, your compounds based on the NMR spectra. And usually, this quantitation is based on the internal standard. So it is known that with NMR, you can get linear response in terms of like using internal standard for the purposes of quantitation with respect to your metabolite signals or your compound signals. It can account for overlapped metabolites also. So um, it one problem also, as mentioned in our previous session, where we could talked about the advantages and disadvantages of the different instruments. NMR usually, if you have compounds that are quite similar, having similar um, signals at a particular chemical shift region, then they will be highly overlapped in that particular region. And so it is very hard to distinguish which is which if you just rely on chemical shift information. And this particular profiling using genomics, as I will show you later on, can actually account for this overlap and still allow you to do quantitation. And the data for chemometric analysis is limited only to, however, yun, yung data that will be obtained is limited to the quantified metabolites. So unlike in spectral binning, you make use of the whole spectra for your data analysis. For your chemometric analysis in profiling, it is limited to the quantified metabolites. So if you only quantify 20 metabolites, your whole chemometric analysis will be only based on those 20 metabolites. Whereas if you make use of the spectral binning, your chemometric analysis will be for the whole range of whatever components are present that has signal in the spectra. So this is just to illustrate. So this is binning. So spectral binning, you divide your NMR spectrum into small bins of about, in this case, 0.02 ppm. And so you take the area for these particular bins, and subsequently it will be converted to something like this. So you see there is a loss of resolution with increasing bin size. So usually you have to, the maximum that is used for NMR metabolomics is 0.04 ppm bin size. If Usually for my case, I prefer to use 0.02 ppm so that you don't lose a lot of the, you don't lose so much on the resolution, especially if you're using 600 megahertz NMR. You don't want to later on make use of too big a bin size that you generate data similar to 300 or 400 megahertz NMR. So you have to optimize this based on your data. And one disadvantage, as mentioned earlier, if you make use of spectral binning, if there are overlapped NMR signatures or NMR peaks, then you won't be able to tell them apart in the spectral binning. And so you make use of profiling in order to um, tell apart those overlap peaks. And this is just a screenshot of the use of Kinomics Profiler in order to do metabolite profiling. And from here, you will be able to see. So, for example, this is the peak clusters for your glucose. You'll be able to match it versus the actual experimental spectrum. And from there, you'll be able to get quantitative data. So you can get the concentrations in comparison to your chemical or internal standard. So in this case, DSS. So again, you get quantitative data, and you para ka nagbubuo ng puzzle actually. So you can match, you try to adjust these peak clusters accordingly. Um, I won't base my quantitation on these peaks kasi nga meron siyang iba't ibang peaks that might also be overlapped with this signal. So I'll make use of the 5.23 ppm peak to adjust yung actual height of the signal for that. And that will correspond to changes also in this region. And from there, you'll be able to like, okay, see ano ba yung contribution of glucose in this particular region. So, it's actually fun to do para ka nagbubuo ng puzzle. Pero if you're working on hundreds of samples, then it's a bit too manual also. So, but yeah, this is it's quite fun to work with. Now, in MS-based data naman, it involves a different range of pre-processing. So, ang MS-based data, especially if you're looking at those data that has been generated together with a separation technique such as GC or LCMS, what you get is three-dimensional data such as this. So, you have three-dimensional data wherein you resolve peaks based on mass to charge as well as based on the retention time and the retention time. So um, data preprocessing is usually done on two-dimensional data. So the first dimension will be the MZ versus the relative abundance at a particular time. So at a particular time, such as like for example 18.5, ano ba yung MS spectra mo? You will have different values, different signals across your different MZ. And so yun yung magko-consist of your MS spectra. On the other hand, you also have the dimension of retention time versus the relative abundance for a particular MZ or for all MZ. So for example, for this particular MZ, like at 200, so meron kang um, uh, extracted ion chromatogram or meron ka ma-generate na ion chromatogram for that particular MZ. Or in the case, if you're looking at all MZ values, then that will be your total ion chromatogram. Okay, so this is just the pre-processing steps that are involved in LCMS based data. Actually, it will also be applicable to your GCMS based data, but there is like another step that we'll talk about for GCMS. So basically, you have your raw LCMS data. You have to perform mass recalibration. Um, it can be using an internal standard or some signal that you can assign in your software. You perform centroiding. When we say centroiding, so usually in high resolution mass spec, you get profile MS data. So that means your signals are collected continuously across. So your signals are collected continuously across through time at a particular interval, and so you will generate a profile MS data. So at very small intervals of MZ, you will get a signal. It's continuous yung scan. But this will generate a lot of data. So masyadong malaking data file yung ma-generate mo if you scan across the MZ. For this particular 300.4 peak, if you make use of profile MS data, so ito nga, continuous yung data na makukuha mo. That's very specific peak widths of depende na rin sa resolution ng instrument mo and your settings. But if you have too much data, the data files are very big. It's very hard to process them, and so usually we make use of centroided MS data, wherein these continuous peaks are converted to like this thin stick or line peaks. And these will be used for subsequent steps of data analysis. And then you can perform feature detection. So this is part again of the algorithms that is usually used in MS-based in MS-based data. You define filtering information. If you make use of a certain threshold, so a certain signal to noise threshold can be used. If you can also define, okay, if this peak is present only in a certain percentage of my whole data set, then you can also choose what you want to do with it. Feature grouping will be more to group similar or similarly behaving ions for a particular retention time. So those that are corresponding to as the same metabolite, but just like for example neutral loss, or they are like adducts of are different adducts, then they will be grouped accordingly. You also have your feature annotation, which will be to provide you with like for example what adduct is formed, and it can also provide initial or tentative identifications based on database search, based on the accurate mass, etc. And at the end, you will have to do alignment. So your chromatograms will be aligned accordingly, either based on a particular internal standard or based on certain algorithms that has been employed for MS data processing. Um, Again, as I mentioned, medyo mas iba yung processing for GCMS data. So kasi 'di ba GCMS data with electron ionization, you get fragments right from the start. So after it has been ionized, nafa-fragment na siya, and that is what goes through to your MS. And so in the cases wherein um, in cases wherein you have overlap peaks like this, you need to be able to determine ano ba yung spectra or yung spectrum for peak 1, ano ba yung spectrum for peak 2, ano ba yung spectrum for peak 3. And that is what is done in the convolution for GCMS. And so there are several softwares, but one of the more popular ones for this, or one of the more popular algorithms for this will be the AMDIS, which is your automated mass spectral deconvolution and identification. So this can be downloaded from the NIST library NIST website. Again, this is usually incorporated in the softwares also already, especially for the vendor specific software. So incorporate na rin nila to for GCMS. So for LC GCMS processing, there are of course your vendor specific processing softwares. So may kanya-kanya silang specific processing softwares. Um, Personally, I've mainly used more of like the SciX ones, like marker view and peak view for mainly marker view for data pre-processing. Agilent will also have Thermo Waters. They will have their own um, processing softwares, or it can be part of the acquisition softwares na. So depende. You also have your open source softwares. So dito na papasok yung mga those that are freely available like XCMS or XCMS Online. So merong XCMS that is mainly based on our environment, and you also have XCMS Online which is very user friendly, and it is web based. So as long as you have the Wi-Fi connection, you can upload your data and let XMS do the data processing uh, online or on the cloud. Other softwares will include your OpenMS, MZMine2, and Metalign, and there's still a lot more. I'm not going through the rest of the. We will not go into so much details for this part, but these are the more commonly used ones. There are still newly upcoming softwares that are being launched. But yeah, so far from what I know, uh, a lot of people are using XMS Online. This is also incorporated in Metabo Analyst, so we'll talk more about that later. Okay, so with advances in analytical technologies and with the use or with the advent of the omics platforms, like we've talked about genomics, proteomics, metabolomics, these different omics generate a lot of data. They are high throughput, they simultaneously measure a lot of different compounds, and this leads to very large amounts of data. And so, what do we do with these large amounts of data? And in order to make sense of that, we can use chemometrics. So chemometrics is actually first coined by a professor in from Umeå University, which is Professor Svante Vold. Just a bit of trivia. Actually, Svante Vold is the grandson of a Nobel Prize in chemistry winner, which is Svante Arrhenius. So if you remember your general chemistry, your Arrhenius acids and bases. So I hope this gets you a bit nostalgic about your basic or general chemistry. So he is Professor Wold is the grandson of uh, Professor Svante Arrhenius. So pinangalan si Professor Wold kay Professor Arrhenius actually. So it makes use of mathematical and statistical approaches to design and optimize measurement procedures and experiments. It can also allow you, yung chemometrics can allow you to maximize the chemical information from analytical data. So it makes use of mathematics, statistics, to make sense of those large amounts of data. So in chemometrics, you usually arrange your data in this particular manner. Although, of course, you can put your samples on the columns, your variables into rows. Pwede naman yon, but usually it is more commonly done such that your variables are on the column and your samples are on the rows, and you can have your class information. So yung class information will be the grouping of your sample. So for example, if you're looking at control versus disease, then your class information will be control or disease. And then your samples has to have unique sample names across variables. This is I think variables that are from chemical shift of NMR data. Sorry, from spectroscopy data. But in terms of NMR, it can be your chemical shift data depending on the bin size. So you can make use of that. In terms of LCMS or GCMS data, this will be your MZ at a particular retention time. So remember, um, three-dimensional yung data that is obtained using MS. So each MZ can have peaks at different retention times. So you need to have um, you need to define for each variable what is the MZ value as well as the retention time. Okay, so you also have what is called data pre-treatment or processing. So meron tayong pre-processing, meron din tayong processing. So dito naman sa data processing, we already process the whole data set in order to make sure that they are comparable against each other. So first, we perform what is known as centering. So it converts the values of your samples, the values for each variable, for each sample to fluctuations around zero rather than around the mean. It adjusts for differences in the offsets of low and high abundance variables. You also have what is known as transformation. So transformation naman, the values themselves are converted. They are transformed into either using logarithmic transformation, or you can use power transformation wherein they are raised to a certain power. So it is occasionally used if you have large values relative to others that will otherwise dominate the analysis. So yun nga, logarithmic, replace x by log of x. When we talk about power transformation, you replace x by x raised to n. And you would also have row processing. So row processing naman across all, so you have different samples. Um, their relative measurements can be will be different. Sorry, their absolute intensities will be different, but you can uh, transform them, you can normalize them in order to make sure that their relative concentrations will be similar. And this will be looking at, for example, if you have slight changes in the mass that is used per sample, then you can also normalize per sample based on the mass or based on total composition of the sample in order to compensate for that slight differences in mass or in composition. Um, you also can use uh, ratio to landmarks, such as the use of internal standards. So you can normalize your samples to internal standards, or even, I think in some cases, you can make use of um, uh, certain signals that are present in your LCMS data, that are not really related to your sample. Others will be your quality control samples can also be used for normalization. And yun. So again, here as mentioned, yung constant total or the sum of the intensities. So total area can be used. Um, Column processing or scaling is also another pre-processing step. So this allows you to ensure that your variables are placed into the same scales. So kasi 'di ba, if you have very high intensity variables, their variation across different samples will also be high compared to very small intensity variables wherein mas maliit yung variation niya. And so if you look at chemometric analysis, some of them generate generate their models based on variations or based on variance. And you can just imagine that if we don't do column processing or scaling, those high intensity variables can actually dominate the model. So you need to put all of your variables, whether they're high intensity or low intensity, on the same scale. And so kaya yun, tinawag siyang scaling. So some examples of column processing or scaling will be your unit variance and Pareto scaling. We'll go into a bit more details into that in a bit. So first, normalization. So again, it is applied to all samples and makes your samples comparable. It removes or minimizes variable dilution effects. Common techniques will include the use of internal standards, creatinine normalization for urine, but please note, creatinine normalization for urine cannot be used if you're looking at comparisons involving disease, kidney disease, for example, because of course we can expect that with kidney disease that your creatinine will change. So hindi siya pwedeng gamitin din for normalization. And another will be your integral normalization or total area normalization, wherein you sum up the total area across all variables for a particular sample and then use it for the normalization in order to get relative ratios versus that total area. There are still other normalization techniques. Some of them are mentioned here, like probabilistic quotient normalization, cyclic Lewis, quantile normalization, cubic spline, variance stabilization, normalization. These are actually normalization techniques that has been previously used for genomics data that are also currently being explored for use in metabolomics data. Okay. In terms of data pre-processing and pre-treatment, so here listed are the different centering, scaling, and transformation techniques. What are the formula that you have to use, and what will they do in with regards to your data? When we talk about heteroscedasticity, okay, medyo big word. It talks about the presence of noise. So we expect that large intensity um, large intensity signals or variables with large intensities will have more noise compared to your smaller intensity signals. So yun nga, scaling methods address these types of um, heteroscedasticity in our data. Okay, the commonly used in my experience in metabolomics, what we commonly use for scaling are unit variance or auto scaling as well as Pareto scaling. So yung first, yung centering, we obtain the mean across a particular variable and then subtract that mean from the value of for that variable for a particular sample. So yun nga, it allows you to center your values around zero rather than around the mean. Um, and then subsequently, these will be divided by the standard deviation in case of auto scaling. And in the case naman ng range scaling, it will be divided by the range. So your X max minus your minimum X value. Pareto scaling will be dividing by the square root of the standard deviation. Vast scaling will be divided by your standard deviation multiplied by your mean over the standard deviation. Level scaling will be divided by your mean. So more commonly used will be your auto scaling and Pareto scaling. Auto scaling in some cases might inflate measurement errors. So it can inflate noise. In order to avoid that, you can lessen the scaling by making use of Pareto scaling instead, which is makes use of, instead of using standard deviation, it makes use of the square root of standard deviation. So this just shows the effect of the different scaling and transformation. So you can see your original data. So you have a few large intensity ones, and there can be like some very low intensity signals. And again, if these large intensity signals dominate your model, then you might get false results. You might not be able to determine ano ba yung significant effects of your low intensity signals. And so it's very important to do proper centering or scaling and or transformation. So here, this just shows you the effects of centering, as well as your unit variance scaling, Pareto scaling, range scaling, vast scaling, as well as the effects of your transformations. As you can see, with untreated, you have some signals that are of very high noise, high variation, and then with transformation, you convert them to you make them more comparable. The variations are only, or the standard deviations are only in a particular range that are common across uh, most of the signals. Power transformation, merong slight effect, pero as you can see, medyo mataas pa din yung standard deviation across certain variables. On the other hand, yung dito naman sa scalings, um, medyo makita mo yung effect ng range, UV, and vast scaling um, in terms of like highlighting those that are smaller intensities. UV scaling does the job. But again, of course, you have to consider that some of these low intensity signals might be your noise. So you need to like make sure that you also don't scale them up so much. So from the data processing, we proceed to the statistical analysis. So this will cover more of your chemometric analysis. So from previously, when we do statistical analysis, we mainly look at the univariate approach. So we determine the significance one variable at a time. So we determine the statistics of one variable at a time, independent of others. Now, this does not fully utilize available data, especially if you're working with instruments like LCMS, GCMS, and you're doing untargeted analysis. Looking at your variables one at a time will be quite tedious if you're going to do it for all of your different signals. On the other hand, if you just selectively identify specific ions, then yun nga, hindi mo nagagamit yung hindi mo na fully utilize yung available data. And so, dito na pumapasok yung tinatawag na multivariate analysis. So this allows you to simultaneously analyze multiple variables or even full spectra. And this can help account for interdependencies of variables. Kasi there can be variables that are related, they can be correlated, or meron silang mga relationships involved in terms of like response, and this can actually help you to account for those. So, multivariate analysis approaches can be divided further into unsupervised and supervised analysis. So, in unsupervised analysis, you will have those uh, that can show ano ba yung mga inherent trends or patterns in the data. So, this is unbiased. So, it doesn't incorporate any class information in its generation of the model. And some examples of these will be your K nearest neighbor analysis, principal component analysis, self-organizing maps, dissimilarity indices. On the other hand, supervised analysis naman, they make use of your class information. So, nagmo-model sila, or they generate the model based on the class or group information that you provide. In some cases, magiging biased siya, and they can be overfitted, and therefore there is a need to always enforce or make use of some validation methods after you have done your supervised analysis to confirm yung reliability ng model mo. Some examples of supervised analysis will include your SIMCA, or soft independent modeling of class analogy, You also have your projection to latent structures discriminant analysis, or PLSDA, and you can also have your orthogonal PLSDA. So these are again non-exhaustive. These are just some of the more common ones. In terms of what I commonly use, it's mainly your principal component analysis. And in terms of supervised, I will usually use either PLSD or OPLSDA. So I'll try to discuss more of those three in these next slides. Okay, so in principal component analysis, this actually allows you to reduce those multidimensional data to a few principal components. So um, what you can just imagine with LCMS data, GCMS data, you generate thousands of variables. And what principal component does is it looks at the variations in the data that is present. So then subsequently, it will group those variations into what is known as components. So uh, the first principal component will be the one that can explain the most variation of the data. The second principal component will then be the next um, group, or it's the next component that can explain the next amount of variation in your data, and so forth, until all the variation in your data has been explained. So it can provide you with patterns, trends. It can reveal the homogeneity of your data. In any inherent clusterings or trends, it can show. And here, just to illustrate, so you have your data set here. You have two different classes here, two different types of samples. Subsequently, from these sorry, from this data set, you'll be able to obtain a projection, and your observation will have a particular projection based on the principal components x sub 1 and x sub 2. Component 1 and component 2. So sorry, this is your axis, this is your principal component. So again, your observations will be projected into your component 1 versus component 2. And then you will be able to have what is known as your scores plot. So scores plot provides you the projection of your samples into the components. So dito, as you can see, you will be able to see whether there are any clusterings or patterns. So you can see clustering of your triangles here. Yung circles mo, medyo distributed siya across the three quadrants here. Loadings plot will be the ones to show you the influence of the variables in the variation. So, loadings plot will be able to tell you ano ba yung mga variables in your data that causes these triangles to separate out from your circles. So, here, you have to look at the same directionality of pictures of your scores and loadings plot. That means kung ano yung mga variables that are in this, kung ano yung mga samples in this region, they are influenced mainly by the variables that are in this region. On the other hand naman, those that are here will be mainly influenced by the variables here. And so, kung ano yung mga triangles nandito, mataas sila in terms of like intensities or levels with the variable x1. Yun namang mga nandito, yung mga circles natin, mataas sila for this particular variable x3. Yung few samples natin dito, they are high in x2. So that is how you look at principal component analysis. Soft independent modeling of class analogy is a supervised analysis. So what happens is you create individual PCA models for each class, and based on the residuals of these models, you'll be able to determine kung saan bang class na bibilong yung sample mo. So It can be asymmetric, such as this, wherein a particular group of samples is isolated from the rest based on its heterogeneity, yung um, PCA class niya. On the other hand, you can also have your two different classes for if you have symmetric cases such as this. You also have for supervised analysis, your projection to latent structures, discriminant analysis. So this discriminant analysis actually can be used to, for example, if you want to determine whether a particular sample belongs in a particular class of samples, then ginagamit tong PLSDA o PLSDA SIMCA. So this is very useful for purposes of, like, for example, quality control. You want to see if you have already established the model for your for good samples as part of your quality control. You would want to see later on if you input data from different samples or from incoming samples, whether they can fit that particular model. So usually yun ginagamit. But in terms of like metabolomics analysis, ginagamit siya for further trying to determine yung mga differentiations as well as the variables that causes these differentiations. So in PLSDA, it makes use of, again, the additional variable or class information. And they try to, in PLSDA, it tries to maximize the separation between your different groups based on the class information that you provide. Medyo may problema siya if you're dealing with high within class, or kung meron kang malaking amount of variations within your classes, then medyo magulo siyang, as you can see, the separation here of your two groups are not clean cut. So hindi siya directly nasa along T1, hindi siya along T2, not clean cut along T3. So yun. So um there can medyo hindi clean yung separation, hindi madaling ma-identify kung ano ba yung mga variables that are contributing to the differentiation of your samples, kasi yun medyo hindi clean cut yung separation of your variables across the different latent structures. But nevertheless, this is useful. As you can see, pwede mo siyang separate. But again, we have to be careful kasi when you make use of class information, it can be prone to overfitting, and therefore, you need to ensure that it is validated subsequently. In terms of the variables important to the projection, this is actually used to identify significant variables that is important in differentiating your different groups. And so if the VIP value, if your VIP value is greater than 1, then it is considered to be important. In terms of orthogonal projection to latent structures, discriminant analysis, this is a variation of your PLSDA. But in this case, you make use of you make use again also of your class information, but you make use of an additional component or an orthogonal component to isolate variables not related to the differentiation of the classes. So kumbaga, sa PLSDA, it just tries to separate your classes as much as possible, regardless of whether the variables involved are related or not to your class information. Sa orthogonal projection, medyo mas nililinis niya. So it separates out those variables that are not related to your class information, and it puts it into an orthogonal component, whereas those that are related to your class information will be put in the predictive component. And so makita mo dito, yung differentiation or yung separation of your two groups are actually along your predictive component. Yung orthogonal component mo, dun na pumapasok yung variations that are not related. So, as mentioned, you need to perform validation. So usually you have different types of validation that can be done. Commonly is performing single evaluation set, wherein 50 to 90% of the samples will constitute what we call the training set. So training set will be the set of samples wherein you base the model, and you will test this particular model with the test set. So this is like the more manual and common and basic validation that is done, single evaluation set. You also have your cross validation set. So what happens in cross validation set is um, your n number of samples are divided into g number of groups, or what we call cancellation groups. And the model is computed g times, and in each time, one cancellation group will be taken out, and this will serve as your test set, while the rest serves as your training set. So each cancellation group will be used g minus 1 times. And when n is used as the number of cancellation groups, it is known as the leave one out approach. So this is the most commonly used validation method. You also have your repeated validation method that makes use of the Monte Carlo algorithm, and is used for it is used to compute many models, and in each model your test set is different, and the variable and you make use of variable number of samples, and it enforces random selection. Medyo mas ano to, this is actually more robust, but it also involves um, more computing power. So relatively, medyo mas commonly performed pa rin yung cross-validation. So in terms of the chemometric workflow, usually yung mga softwares, yung isang software mo will cover your data pre-processing and data extraction. As we have seen, we have MZMine, XMS. I think XMS actually also already have XCMS Online already have like some statistical analysis incorporated in their web-based platform. But I usually don't make use of them. I still use it mainly for data extractions, and subsequently I still do some cleanup offline, and make use of either SIMCA or Metabo Analyst for the chemometric analysis part. And yun, so meron kang software for processing. You can also have your software for the chemometric analysis. And yun nga, as I mentioned, in some cases, you can make use of one web-based platform to perform everything. So it can be your XCMS, it can be your Metabo Analyst, or in vendor specific software will be your MPP for Agilent, and so on. So again, these are the chemometric software tools that you can use. Metabo Analyst is a web-based platform. It's open source. You can do code-based analysis using R, Python, MATLAB. SIMCA is a commercial chemometric analysis software. Minitab, SPSS are statistical analysis softwares that also has some of these chemometric functions. We'll go a bit further into Metabo Analyst. So again, this is actually a web-based platform that is mainly for metabolomics data analysis, although you can use it for the chemometric analysis of other types of data. So actually, it is like a one-stop shop. So you can input certain formats of data, of LCMS data. It can do the initial LCMS spectral processing, and then you can do some functional analysis or meta-analysis. It has features or functionalities for enrichment, pathway, joint pathway analysis, as well as network analysis. If you have gene, metabolite data, it can do network analysis on those types of data. It can perform your statistical analysis, biomarker analysis. It can do two-factor or time series analysis, statistical meta-analysis. It can perform power analysis to determine what will be the suitable experimental designs, and it has other utilities. So, makita mo, yun nga, one-stop siya for a lot of the different things that you need to do for metabolomics data. And it's actually developed by the SIA group in McGill University, and actually it's part of the Metabolomics Initiative Consortium of or the TMIC of Canada. So these are developed by Professor Xia, Professor Wishart, and the rest of their group members. Um, this is just to show you an example of PCA using metaboanalysis. So at the start, you'll be able to get this overview plot. You'll be able to see which components shows you the separation of your different samples. And then subsequently, you can look at your score plot. So here again, you will be able to see inherent trends or patterns. So in this case, your B and D are clustering together. So they're basically similar in profile. Your A and C are clustering separately. In terms of variables that are influencing their separations, you can look at the biplot. So you can look at the loadings plot, but for easier reference, you can also make use of the the biplot, wherein it shows you the scores, your samples, as well as the variables. So from here, you'll be able to see that A samples are actually high in variables like V22 and V7. Those that are your C samples are high in variables such as V42 and V27. Your B and D samples are high in variables such as V10, V24, V1. So again, reflecting the directionality of your scores and loadings. Um, Metabo-analysis will also allow you to perform other types of statistical analysis. So this is just for the statistical analysis module. Marami pa siyang ibang modules. So you have your biomarker module, your time series module, etc. etc. So there's really a lot of functionalities here. I will not have time to cover all of them, but just to show you, you can perform your basic univariate analysis. You can have correlation heat maps. Heat maps are actually very useful to show patterns in your data, and they are usually used for visualization of your data of metabolomics data. And of course, you will have your chemometric analysis functionalities like PCA, PLSDA, sparse PLSDA, and orthogonal PLSDA. There are also some more advanced feature identification functionalities such as SAM, EBAM. I think some of them might be more suited uh, uh, for time series, but in any case, again, these are features that you can make use: heat maps, SOM, k-means clustering, and also you have a bit more of the more advanced algorithms such as random forest and support vector machine algorithms. And while you are making use of this, you also generate your R commands. So again, so actually this metabo analysis is R based. So whenever you make use of any functionalities, it is actually calling out a particular function in R. And so you can actually save this, and you can make use of this for uh, s- later if you want to like rerun the analysis. So after sorry, after the statistical analysis, you then perform metabolite identification. So in GCMS data, again, we have mentioned that you in with the electron ionization MS data that you generate, you can actually use it for matching with databases such as your NIST library. For proton NMR data, you can identify compounds based on chemical shift and multiplicity of peaks. Kapag medyo mas overlap na, pag mas complex yung mixtures, of course, that will be a bit difficult, but you can also make use of 2D NMR and yung functionalities nga ng kinomics na profiling, which is yon sa mga analysis of mixture functionalities of softwares. You also, for LCMS naman, you can, if you're making use of high resolution MS, you can do putative identification based on accurate mass, and you can also use the fragmentation information that you obtain using MSMS. So ito, yung putative identification based on this can be for either your LC or your GCMS. But again, for GCMS, meron kang additional dimension of identification based on the fragmentation generated using electron ionization. And actually, I forgot to mention here, but another thing with GC data, you can make use of your retention time index. And when you're referring to NIST library, having that retention time index information can actually help provide you with more reliable identification of your compounds. So this is just to show you an example of like from your chromatogram, you can identify at a particular point your mass spectra for that particular peak. And from there, you'll be able to search the database, the NIST library for possible identities of that peak. And so from there you have to like of course you need to assess kung ano ba yung level of matching niya. The software will provide you the scores based on the match, but of course you also need to sometimes check and confirm na ayos ba talaga yung match, because there are times that they might not be really matched in some cases. Pero so yun. Okay. So these are the databases that you can use for the identification of metabolites based on accurate mass. So you can input accurate mass, and you can search through these different databases for possible identity. Some of them will have some experimental MSMS data that you can also use for matching. They also have functionalities to allow you to input MSMS data, and yun nga, para magawa yung spectral matching mo for MSMS for further identification. So some of these will be your methylene. So methylene is developed by the same group that developed XCMS. You have your human metabolome database. So this one is more on the Canada metabolomic side. You have your mass bank. So mass bank has a Europe and a Japan consortium. So you can make use of their databases as well. And you also have lipid maps, more for lipids. In terms of levels of metabolite identification, of course, highest level will be your identified compounds, wherein you analyze authentic reference standards or standards, and you identify based on a minimum of 2 independent and orthogonal data, such as your retention time information as well as the mass spectra. And you can also have your MSMS spectra. Level 2 will be your putatively annotated compound. So you can from metabolomics papers, you will see a lot will mention putative identification. So the putative identification is usually based on spectral data or similarity to data that is available in public databases without confirmation to reference standards. So yun. Level 3 will be putatively characterized compound classes, like for example, lipid classes. They are unidentified, but the data available allows the metabolite to be placed in a compound class. So, for example, presence of certain functional groups will be attributed to a particular class of compounds. And so, the presence of those functional groups can actually, or signals that can be attributed to certain functional groups can allow you to assign some of these compounds to a level 3 identification. And of course, level 4, there are um, from the many data that you generate in metabolomics, there will always be bound to be some features that you will not be able to identify, and they can be differentiating, but they cannot be identified, so they are level 4 classified, or they are unknown compounds. So, in terms of these levels of metabolite identification are actually defined by the chemical analysis working group of the Metabolomic Standards Initiative. You can refer to their publication in terms of the minimum reporting requirements for metabolomics publication. So this is actually a very useful guide if you're starting out in metabolomics, because it helps you to determine ano ba yung mga kailangan mong i-consider. It can also give you information on ano ba yung mga kailangan mong i-record, ano ba yung mga main considerations, etc. So please do check out this publication. In terms of pathway analysis, there are different softwares that you can also use. These are actually more of the open source ones. This KEGG is actually a very well-known pathway database. This is Kyoto Encyclopedia of Genes and Genome. Sorry if I have made, I'm not very sure, but it's something close to that. So that is KEGG. So it provides you with the pathways for different, the whole networks of pathways for different organisms. And it's actually a very useful database. You also have this one naman is more of the commercial uh, Qiagen Ingenuity Pathway Analysis. This actually allows you to incorporate or to integrate genomics, proteomics, metabolomics data. As you can see from here, do network analysis. It can do multi-level analysis of your gene expression, proteomics, metabolomics. Although it comes at a very steep price. I tried inquiring for one of these, and it costs thousands of dollars to have 1 year subscription. So medyo yun, it's one consideration. You have MetaPsych, also another pathway database that you can make use. And of course, you have MetaboAnalyst that can perform, wherein you can perform your pathway analysis. So this is just to show you a screenshot of pathway analysis with MetaboAnalyst. You can input compound lists or concentration tables showing your different variables or different compounds. And then you have your samples as well as your class information. And this can be used for for the pathway analysis. You can also make use of data that are available in if you want to look at the pathway analysis of data that's available in their metabolomics workbench database, you can also do that. For this one, I just inputted the example data. So if you want to practice using MetaboAnalyst, they have some example data that you can use for practices. And so from there, you'll be able to determine ano ba yung mga significantly perturbed pathways based on the significance values, as well as the number of metabolites that are in your list that are in these particular metabolic pathways. And from here, you will be able to have the visualization. So higher, closer to the upper right, the more important and the higher impact they are. And if you click on one of them, you'll be able to see yung diagram of that particular metabolic pathway. The information, yung number, those that are in red are actually the ones that are in your compound list. So ito yung mga nasa compound list mode that are present in that particular pathway. And the numbers here are actually the KEGG metabolite IDs. Recently, there are a lot of there are a lot of improvements or advancements in terms of molecular networking. So LCMS, GCMS, and targeted metabolomics, you generate a lot of data, you do chemometrics, you only identify the compounds. You only try to identify the metabolites that are found to be significantly different or significantly differentiating. And so with that, you limit yourself. I mean, um, the rest of the data is not used. So kumbaga na di-discard na or nawawalan na ng gamit yung the rest of the data. But actually, especially in the era or in the area of natural products research, they can actually be very useful. So currently, these organizations try to get as much of these LCMS and LCMSMS data, and from there try to establish, kasi di ba, when we look at fragments, these can actually have information on characteristic functional groups. And so this information, if can be useful in the identifying certain moieties present in a particular compound. Um, so in molecular networking, they make use of those data to identify, for example, in this case, for this group of stenotricine compounds, all those ions that are close to these stenotricine compounds actually have fragmentation patterns that are close or similar to these identified compounds. And so there is a possibility that they can be analogs or derivatives of these compounds, even though they are not yet identified. So dito papasok yung the use of molecular networking, and this can actually be very useful in the long term, because from here you will be able to build databases of MSMS data, and this might lead to further identifications of different compounds by through the use of molecular networks. Um, okay, so the last part of the metabolomics workflow is, of course, validation. It is good to have
Si din ba
biological
yan? Si Donald din ba to?
experimental validation of your studies. It helps to corroborate preliminary results and consolidate the biological interpretation of your studies. You can have external validation wherein you make use of an entirely new set of samples that are collected and processed, or you can also have internal validation wherein samples that are obtained from the same study can be subjected to targeted analysis. So kung initially nag-conduct ka ng untargeted metabolomic study, you have identified the significantly perturbed metabolites and subsequently the pathways. You can then do a more focused analysis or a targeted analysis of those specific pathways and metabolites using the same set of samples. So that is internal validation. You can also have independent specific studies. So for example, if you have done an in vitro study, those metabolic pathways that you have identified to be significantly differentiating, you can look at it in an in vivo or in humans, and vice versa. So these are the different types of validation techniques that you can make use of. And so please do stay put. We have one more speaker coming up. So we'll be hearing from Dr. Rod Sumayaw on his applications of metabolomics in clinical studies. So that will be a very exciting presentation up ahead. Acknowledgements, of course, much thanks again goes to the OST, PCHRD, and the Balik Scientist program for sponsoring my Balik Scientist journey here and allowing me to be part of this program. It is an honor. It's a very it is a privilege, and I'm really grateful for that. De La Salle University Manila for hosting me, for Professor Drexel Camacho for being the one who has invited me over and has introduced me to this Balik Scientist program. The LSU CIF staff who has been behind the scenes on all of the works involved in this webinar series. Thank you very much. You guys are really great. And shout out to Chris, to Alona, to Hazel, Jeka, Jude, Sir Veer, Sir Jojo, to the whole team for all the work that you do for this webinar series. To our guest speakers, Dr. Pekka Lingasyon, Dr. Melo Syria, and Dr. Rod Sumayaw for agreeing to be part of this webinar series. To the research control, I just would like to give a shout out. Uh, I'm not sure whether this will reach them, but A big shout out to researchers and consortiums working towards open source databases and software solutions for metabolomics. A lot of researchers will not be able to do their work given, like, of course, funding issues. So these open source softwares and open source databases are very useful and very instrumental in a lot of the work that we do. And of course, much thanks to families and friends for the ever constant inspiration and support. And lastly, thanks be to God. All praise and thanks be to God for His wonders and His grace. And that's all, folks. If you have any questions, if you need any help, if you want to pursue metabolomic studies, and you need help, please do let me know, and I'll be very much happy to help out. So that's all.
And thank you, Doc Karen, for the very enlightening talk. Congratulations also on ending your discussion series on a high note. We're really very lucky to have you. So, ang dami nating natutunan from the introduction to metabolomics, yung 2 parts na yun, up until now, yung sa discussion ni Doc Karen on the chemometrics in metabolomics. So, to recap her talk on chemometrics in metabolomics, we were introduced to data pre-processing using NMR. So, meron tayong spectral binning versus profiling. You also have the software which can be used. So that was also introduced. For MS-based data pre-processing, this was done on 2-dimensional data. We were introduced to the workflow. The convolution, centering, normalization, scaling, transformation techniques were also introduced. The advantage of a multivariate analysis was also emphasized briefly over univariate analysis. Under multivariate analysis, we have unsupervised analysis like the PCA, or the principal component analysis, which we saw earlier had a lot of applications, and supervised analysis like PLSDA, OPLSDA, and SIMCA. So including validation and the overall chemometric workflow. So the one-stop shop software Metabo Analyst for chemometrics in metabolomics application was also introduced, and metabolomics workflow was also reviewed. Levels of metabolite identification, pathway analysis, and lastly, molecular networking were also discussed. So yun, there was really a lot, but if you want to review the information which was presented, including the information presented in the past 2 meetings or the past 2 sessions, just head over to our Facebook page live section for the uploaded recording later after the webinar. So ayun, actually nakita niyo na siya. Anong oras na? It's time for another surprise quiz with our surprise prizes. Hindi na siya surprise kasi same lang tayo ng prizes as last week if you were able to attend. For the 2 winners, there will be 2 winners again of the DKSH work from home package na secret pa rin actually until now. So yung winners natin from last time, hindi pa rin nila alam kung ano yung paparating sa kanila. So we will be sending these to you soon. Wait lang po tayo. And yun, again, stretch na po tayo ng fingers para ready tayo mag-type for the questions that I'll be asking. So mechanics, this is open to all who registered in the webinar. So I'll be asking you later kung nag-register kayo. So you will be disqualified if we check na hindi pala kayo nakapag-register. So please kindly check if you were already registered before answering. There will be 2 winners of a smart load card worth 500 pesos. By the way, one winner from last week wasn't able to claim his card. So ipapasa natin to this week's session yung premyo na yun. And there will be again 2 winners of the DKSH work from home package. We will also be asking a question. And the first one to answer will be asked to turn on his or her camera. So pag sa Zoom, pag di nag-on ang camera at mic para ma-interview, hindi ma-awardan ng prize. We will be monitoring both Zoom and FB Live. So lastly, to claim your prizes, so medyo iniba natin yung rules, winners must message our Facebook page. So that's DLSU Central Instrumentation Facility at the end of the program. So for the questions, mag-start na tayo. Okay? So this is question number 1. And this is for Zoom participants. You can win a 500 peso load card. Sorry, by answering this question. So Yan. So, ready na tayo Question. The CIF is under the umbrella of which DLSU office? Again, the CIF is under the umbrella of which DLSU office? So, type nyo na po yung sagot for Zoom participants. So again, the question is, sa anong office napapabilang ang DLSU CIF? So you must be familiar with the organizational structure of De La Salle University for you to be able to answer this. So far, ang mga sagot po natin ay Binyan, DLSU Laguna. No po, we're not pertaining to the campus, we're pertaining to the office. Okay? Which particular office of DLSU is CIF under. Ayan. So we actually presented this a couple of times. Yes, Vice Chancellor, medyo malapit na. Okay? Medyo malapit na po tayo. Vice President for Research, close enough but not quite. Ayan. Pag hindi po nasagot, OVC for Research. Sige, I think okay na to. Okay, so the correct answer, Hazel, please, is Office of the Vice Chancellor for Research and Innovation. So the first one to answer, OVC for Research was Amster Bakiran. Hi, Ams. She was also she's also a student at DLSU. So, kamusta?
Okay naman.
Okay naman. Buti naman, okay ka. Nakapag-register ka ba sa ating webinar earlier?
Ay,
Oo naman.
ba? Dapat.
Kailangan registered. Okay. So, yan, kung registered ka, may check naman natin yan. You will be awarded the prize. So, thank you so much for joining. I will be sending you the details later. Thank you. Okay. So, thank you, Ams, and thank you everyone for joining the first contest natin. So, the second question is for our Facebook participants. So, yung mga nakatutok sa live stream, mag-ready na kayo mag-type. And so you will be winning a DKSH work from home package by answering this question about the history of chemometrics. So chemometrics po yung topic natin. Okay, so ito yung tanong natin. This Nobel Prize in Chemistry winner, who was also the first one to introduce the concept of global warming from a physical chemistry perspective, also has a physical chemistry equation named after him, which describes the formula dependence of reaction, temperature dependence rather, of reaction rates. So another clue, his grandson, Svante Holt, coined the term chemometrics. So who is this Nobel Prize in Chemistry winner? Na lolo ni Svante Holt na nag-coin ng term na chemometrics. So very, very quickly, can you open your mic, Mr. Garil J? And yung video mo rin. Ayan.
Hello po. Hello.
Dito po. Hello. Kamusta, sir? Saan po kayo?
Sila po.
Nasaan po kayo ngayon? Sa
Osamis.
Wow. Okay. So, kamusta dyan, sir, sa Osamis? Sana okay kayo.
Okay
ang sagot niyo po ay Arhenius at tama po kayo. Ayan. So, the person we're pertaining to is Vante Arhenius. Thank you, sir, for joining. Okay.
Salamat.
Kindly message us sa Facebook page to claim your prize. Okay? Thank you.
Okay.
And then for the third question, this is for our Facebook. I'm sorry. Ay, sir, sorry Sorry, Sir Garil J. Zoom pala kayo. So we'll need to ask someone or check someone from the Facebook page pala. So I'm really sorry about that. So I'll have to check yung Facebook stream natin kung sino po yung unang nakasagot nun. So ang una pong nakasagot from our Facebook stream, hopefully you're still tuning in. This is Mr. Jason C. Alcano. Okay? So Mr. Jason Alcano, if you're watching, kindly message us to claim your prize. I'm really sorry about that, sir. Okay? So moving on to our next question. The next question is on we'll be winning another DKSH work from home package. So this is the next question. For the third question, this is about the DLSU chromatography lab. So the question is, what specific type of chromatograph is coupled to the quadrupole time of flight mass spectrometer or QTOF LCMS? Again, what specific type of chromatograph is coupled to the QTOF LCMS of the DLSU CIF? Okay? So yun po yung tanong natin. This is for the Facebook participants. Okay, so wala pa po tayong, and I'm monitoring right now. Again, what specific type of chromatograph is coupled to the quadrupole time of flight mass spectrometer ng DLSU CIF? So, ayan, meron bang sumagot? Wala pa yata. Okay. So pag wala pong sumagot in the next minute from our Facebook page, I will be passing this to our Zoom participants na. Okay? Yung question. Okay? So again, ang tanong po natin, anong chromatograph? Okay? So clue, meron po siyang LC sa pangalan. So hindi yun yung buo. Okay? So going once, twice, wala pong sumagot ng tama sa ating Facebook live stream. So I will be passing this to the Zoom. So starting now, you can answer ano po yung sagot natin doon sa question. So may mga sumagot ng HPLC, close but not quite, pero very very close na kayo. So I'm looking for a very specific configuration ng HPLC. Ayan, actually. Mas malupit pa si HPLC ito. Ayan, yun po yung clue. Okay. So since running out of time, actually the answer is, yan, actually may nakasagot. Okay? So Mr. Michael Serafico, can you open your mic and video camera please? Hi, Sir Michael.
Yes.
Ayun po.
Chris.
Ano pong sagot natin? Sorry, sa question. Ano po yung naka-bundle or naka-couple doon sa ating QTOF LCMS? Ang sagot niyo po ay
UPLC.
UPLC. So, ultra
performance.
Ultra performance liquid chromatograph.
Liquid chromatograph.
Ayan. Okay. So, very good, sir. Thank you so much. Kindly message us sa Facebook page to claim your prize. Okay? Thank you. Right?
Thank you.
For the last question, this is for the Zoom participants na, okay? The question is related to Dr. Rodolfo Sumayo Jr. Medyo related, okay? So if you've seen our our infographics, you've seen that Dr. Sumayo earned his PhD from the University College Dublin in Ireland. Now, the question is not really related to Sir Rod himself, but to Ireland. What is the name of the Irish pop rock band formed by siblings and cousins which became famous in the late 90s and early 2000s? They are composed of 4 members and they composed and sang the songs Runaway, Breathless, and All the Love in the World. Okay? So Miss Miss Marilyn Miranda, can you open your mic and video please?
Yes.
Ayun po. Ano po yung sagot natin, ma'am? Kamusta po kayo dyan? The course, okay? Ayan. Wala pong judgment sa edad. Okay lang po yan. Ako po yung gumawa ng tanong. Yan, na-judge din ako. Okay, thank you so much for joining, ma'am, and congratulations for winning. Kindly send us a message via Facebook to claim your prize. Okay, thank you so much. Okay, balik tayo doon sa ating program proper. Okay, for the next part of the program, live siyang magpe-present later. We will be welcoming another accomplished research scientist in the field of metabolomics. He obtained his PhD in biochemistry at the University College Dublin, Ireland, and his doctoral studies focused on the role of reactive oxygen and nitrogen species in the kidney dysfunction associated with rare genetic disease, cystinosis, with funding support from Cystinosis Ireland and the American Cystinosis Research Foundation. He later pursued postdoctoral studies in UCD Conway Institute, Dublin, investigating the role of nitric oxide in the molecular pathophysiology of renal disease associated with cystinosis using state-of-the-art proteomic and imaging platforms. This project was supported by the American Cystinosis Research Foundation. Currently, he is an associate professor at the chemistry department of De La Salle University, Manila, Philippines. As a principal investigator, he leads a research project aimed at characterizing the breast milk metabolome of Filipino lactating women and how this influences health outcomes of their breastfed infants. So very important research. He is also actively involved in the studies investigating the effects of bioactive compounds from local endemic berries on cancer-associated signaling pathways. So without further ado, let us all welcome Dr. Rodolfo Sumayaw Jr.
Thank you, Chris, for that warm introduction. Before anything else, I'd like to know, may I ask if everybody could hear me?
Yes. Yes, sir.
Okay, thank you. Can everybody see my presentation as well?
Yes.
Okay. Pleasant morning to everybody. I am delighted to be serving as one of the guest speakers for today's webinar. And I think I should acknowledge Mr. Chris Argamino for including me in his quiz. Well, not related to me, it's the course, okay? And one of the popular bands in Ireland. Quite interesting because I bumped into them in one of the popular bars in Dublin. So very, very nice band. It's actually one of my favorite bands. Also, I think I'm quite fortunate because Dr. Lacerna presented before me, and Dr. Lacerna did an excellent presentation on essentials of metabolomics, which are also employed, okay, in metabolomics, clinical metabolomics. So that is going to work to my advantage, okay, because I don't have to discuss them in greater detail. So, but nonetheless, I'm going to mention them as part of my talk this morning, okay? So now for this presentation, I'm going to talk about the application of metabolomics in the clinical setting. Hence, I entitled my talk as Metabolomics, Bridging Basic Research and Clinical Medicine. This will be the outline of my presentation. So initially, I'm going to discuss an overview on metabolomics. I know you've had a lot of, you've got an overdose or quite practically saturated with metabolomics, and you pretty much know the definition of metabolomics at this stage. So I'm going to reiterate that as part of my presentation. And just earlier, Dr. Lacerna had this brilliant presentation on the various tools and strategies in metabolomics. In fact, Dr. Lacerna highlighted the typical workflow on untargeted metabolomics. And I will also go past, discuss it very quickly because it will form important part of my talk this morning. And the highlight of my talk would be the application of metabolomics in the clinical setting. And toward the end, I shall discuss the applications, my research initiatives, my personal experience in metabolomics, specifically with emphasis on applying this field in studying the complement of metabolites in this biological fluid, the breast milk obtained from the Filipino lactating women. And lastly, I'm going to present the summary of my talk. So I suppose you're very familiar with Oliver Fien at this stage. Okay, so Oliver Fien is considered the father of metabolomics. Okay, and he proposed a lot of developments in metabolomics. In fact, he has over 200 publications to date in metabolomics. He now serves as a professor in UC Davis, and is also the current director in a very well-known metabolomics research center, Analytical Services and Metabolomics in US, the NIH West Coast Metabolomics Center. Now, by definition, metabolomics involves or refers to the screening of small molecules that we call metabolites that are present in biological samples or biological fluids. Now, you may wonder how small these molecules are. Okay, so generically, these molecules must be less than 1,500 Daltons. Okay, now the complement of these metabolites, or the inventory of these metabolites is what we call the metabolome of the organism. Therefore, the metabolome of this organism can provide a snapshot of the metabolism, and this is also widely recognized as the biochemical or the molecular fingerprint of the organism. Hence, the metabolites or the inventory of metabolites in an organism can provide the biological and health state of an organism. And this is practically where my presentation this morning will revolve around. Now, metabolites comprise an enormous chemical diversity of compounds, okay, organic compounds. They can be sugars here, okay, amino acids. They can be organic acids. You have the nucleotides, acylcarnitines, and lastly, the lipid metabolites. And they present several differences in their concentration in biological fluids. Therefore, in the current technological conjuncture, the use of more than one technique, okay, is indispensable in order to analyze the highest proportion of metabolome, okay, as well as its concentration, its identity, and to seek an efficient construction of metabolomic profile. Now, however, the question is, which among these metabolites are actually considered part of the metabolome of the organism? It remains controversial until now because it results in partly confusing definitions. Okay? For one reason, the metabolites present in biological systems such as this, okay, they are defined as the metabolome in a very strict sense if they are endogenously synthesized, meaning they're synthesized by our body, by our cells. Okay. However, there are also metabolites that are exogenously derived. Okay, so these are what you call xenobiotics. Now, metabolites from the xenobiotics could also include the phase 1 and phase 2 metabolites, which arise from the further metabolism of the xenobiotics by various tissues and cells in our body. And the complement of these xenometabolites, including their phase 1 and phase 2 intermediates and metabolites, are what you call the xenometabolome. And this is what makes metabolomics a particularly difficult field because of differentiating between a xenobiotic or differentiating between a xenometabolome and the endogenous metabolome. However, to avoid confusion, I shall focus only on the endogenously obtained metabolites. So this is the traditional metabolomics. And perhaps you've come across this diagram highlighting the series of omics disciplines over the past couple of years, okay? And metabolomics here, if you can notice at the very bottom, is one of the omics science that is relatively new, okay? It's fairly new. It is still in its incipient stages of development here in the Philippines. I can only name a few who does metabolomics work and studies here in the country. And we are lucky that we have Dr. Lacerna as a balik scientist because she can actually provide direction to the metabolomics studies in the country. So one of the advantages of doing metabolomics is that there are only relatively few metabolites in biological system. If you compare that with the number of genes we have as predicted by the Human Genome Project, we have about 22,000 genes, okay? While the transcriptome that arise from the genome, okay, these are mainly RNA, a complement of our RNA species, we have about 100,000 transcripts or mRNA transcripts. Now, the translation of these transcriptome or transcript leads to the complement of all the proteins in an organism, and we call this proteome. Now, the field of study that deals with the organism's proteome is what you call proteomics. And interestingly, okay, we have a lot more proteome in our body than our genes. So it is predicted by the Human Genome Project that we have 1 million proteoforms or protein isoforms, and many of which remain unidentified. Okay. And however, okay, the metabolomics is actually in a very good position because due to the advancements in analytical instrumentation such as mass spectrometry and nuclear magnetic resonance spectroscopy, many of these metabolites, more than 5,000 of them, are well characterized now. Okay. And interestingly, there is a subset of metabolites that capture the interest of many other researchers, such as the lipid metabolites. Okay? Now, these lipid metabolites form at, around 30,000 species of them. So they are quite diverse. Okay? And the study of these lipid metabolites, okay, are what you call the lipidomics. Now, compared to genomics and transcriptomics, as you can see from this figure, okay, the metabolomics can actually directly or what you say accurately reflect the current status of the organism. And they can tell us what exactly happened to the organism because this is the ultimate manifestation of the changes in the gene expression exactly from this stage of the transcriptomics and proteomics, okay? And in other words, the inventory of all these metabolites, in thousands of them in an organism, can reflect the downstream activity of your genes. I'm referring to the genome. Okay, the proteins, I'm referring to the proteome, and also can offer a high level of functional description, okay, that transcends pure genomics, transcriptomics, and proteomics. That is why many researchers now are doing integrative omics, okay, in studying disease mechanisms, wherein they try to integrate their genomics, transcriptomics, and proteomics data with the metabolomics data, okay, to create a complete story of the disease mechanisms of an individual. And now it is now possible in a systems context. Dr. Lacerna mentioned the Metabo Analyst, which is a publicly available software that you can use to do integrative omics. It is now one of the advances in metabolomics because you can do integrative approaches. You can integrate various omics data with your metabolomics data to arrive at highly functional biological interpretation of disease mechanisms. And moreover, the rapid evolution of machine learning methods, some of which have been described by Dr. Lacerna, at the same time, artificial intelligence in the last 5 to 10 years has enabled accurate analysis of these metabolites. Okay, so we can now analyze large data sets of metabolites, and this leads to an avalanche of biomedical information. If you look at the PubMed in the past 10 years, you can see that the metabolomics data are growing in numbers. There are hundreds of papers being published in metabolomics, okay, over 5 or 10 years and possibly in the next years to come because of the advancements in analytical instrumentation, as well as in machine learning or vector learning methods. Now, as I mentioned, the metabolomics target the screening of these metabolites. Okay. Now, the quantity as well as the qualitative aspect of these metabolites are very important. Okay, because they appear to be very responsive to various stimuli. Okay, what are these stimuli? It is shown in this slide. This could be genetic or epigenetic stimuli. This could be environmental stimuli. Okay, and also physiological stimuli such as age. Okay, and other factors such as drugs, okay, nutrition, and lifestyle could also strongly influence your metabolome. And because of the sensitivity of these metabolites to various stimuli described in this slide, metabolomic disturbances have been associated with many disease mechanisms that includes cancer, diabetes, and cardiovascular diseases. So if you look at the literatures, several metabolomics actually look into applications of metabolomics, look into the disease mechanisms, targeting biomarker discovery or discovery of panel of metabolites that can actually indicate whether a disease is happening or could also be used for personalized medicine for diagnosis and prognosis of diseases. And also the metabolome is unique. It is dynamic and it is related to the phenotype of the organism. As I mentioned in the previous slide, many researchers are recognizing now metabolome as the ultimate phenotype of the individual. That's why it is now in a very good position in the era of biomedical science. Okay, and usually the ultimate goal of metabolomic is to perform high level interpretation or biological interpretation. And this is true for untargeted or discovery metabolomics. So earlier, Dr. Lacerna discussed the approaches in metabolomics at targeted and untargeted metabolomics. Now, the untargeted metabolomics is one of the most established approach in metabolomics, especially for the purpose of biomarker discovery with applications in the clinical setting. Okay. Now, this leads us to the traditional tools and strategies that are employed in metabolomics. And there are two. I think this has been mentioned by previous speakers and highlighted by Dr. Lacerna as well. So as I mentioned, I'm very lucky because I don't have to discuss this in greater detail. But I'll try to highlight some bits and pieces with emphasis on its application in the clinical setting. Okay. So first is the untargeted metabolomics. Okay, so what's untargeted metabolomics? Sometimes they call it global metabolomics because you're actually looking at all the complement of the metabolites or biochemical features in biological fluid. And most recently, scientists call them discovery metabolomics. Okay, now discovery metabolomics involves unbiased screening of metabolites in biological sample. I would like to highlight the word unbiased. Okay, bakit kaya unbiased? Because you're actually using stringent data analysis to arrive at a conclusion. Okay, so you need to be able to identify these metabolites in an unbiased manner using various methodologies, analytical and also computational methodologies. And the goal, one of the goal of discovery metabolomics is to compare the patterns or profiles of metabolites among different sample groups. You may compare, for example, healthy cohorts and disease cohorts with cancer, with other non-communicable or communicable diseases. Okay, and also, discovery metabolomics involves simultaneous detection of these metabolites. That's why it is important that you use highly sensitive, highly reproducible analytical instrument for this. Okay, it involves comparing the metabolome between your experimental and control group, and you want to spot differences between their metabolite profiles. So that's actually the goal. And I think that was discussed by Dr. Lacerna as well. You do functional or pathway analysis, and eventually you validate these. Okay, so that eventually they can be applied as biomarkers and they can be validated in the clinical setting. Okay, and usually, okay, the goal of untargeted metabolomics is to perform high-level functional description or biological interpretation of these dysregulated metabolites. When you say dysregulated metabolites, I'm referring to low upregulated. Okay, those are metabolites that are above the normal levels, or the downregulated. These are the metabolites that are below the normal or physiological levels. Okay, and these dysregulation in metabolites could actually be related to you could actually relate it to a mechanism of disease, such as cancer or any other diseases for that matter. It could be communicable, okay, such as infection, or non-communicable, such as cardiovascular diseases. Okay. Now, the second approach is targeted metabolomics. Okay, so the keyword here is target because you're just looking at a specific panel of metabolites. In fact, okay, in targeted metabolomics, you're actually focusing on the validation of selected metabolites that you discovered that are dysregulated from the discovery approach. Okay, and when you say validation, as mentioned by Dr. Lacerna, you need large numbers of samples. Okay, because these large number of samples can be used to explain the effect of natural and biological variation in validating the identity of these previously identified metabolites. And I should mention that variations, either induced or uninduced, is actually rampant, okay, in metabolomics data, because metabolomics data is a multidimensional data. So by nature, this data is actually laden with a lot of variations, especially when you're dealing with individuals, okay, human population, because there are inter-individual differences, okay? Now, for that matter, you need to use large numbers of samples I highlighted here in targeted metabolomics to account for this variation. Okay, so I think that was mentioned by Dr. Lacerna as well. Okay, the induced and uninduced, making your data heteroscedastic. This is what you call the heteroscedasticity of metabolomic data. So in essence, okay, the targeted metabolomics emerges from the global screening of metabolites via the untargeted approach. Okay, and usually, if I may highlight, targeted metabolomics explore metabolites that are related to a specific pathway. For example, pathway for the metabolism of inflammatory lipids. Okay, so typically researchers would look at the various metabolites and intermediates that are involved in the metabolism of these inflammatory lipids. Okay, and oftentimes analytical and system biology approaches are used by the researcher as they look into the concentration, bioavailability, turnover, metabolism, and very importantly, the regulation of these metabolites. Okay. So, meron ka pa ring functional interpretation, high-level functional interpretation sa targeted metabolomics. It's not only routinely done in untargeted metabolomics. Now, this is the traditional workflow or the typical workflow for untargeted metabolomics. This was discussed in great detail by Dr. Lacerna. I enjoyed her talk, and I'm actually quite smiling behind the camera. Sabi ko, I don't need to discuss this in detail because we had such an excellent and brilliant presentation from Dr. Lacerna about this workflow. Nonetheless, I shall briefly describe this as it is applied in the clinical scene or setting. Okay. Now, the untargeted metabolomics typically involves these steps, okay? Profiling, okay? You have the profiling, you have the compound identification, okay, here. You have biological interpretation at the very last panel, okay? Now, I should include statistical analysis. It was discussed in detail by Dr. Lacerna. It is actually part of the chemometric analysis. Okay. Now, traditionally, chemometric analysis in metabolomics would involve this: okay, baseline correction, peak alignment, normalization, deconvolution. But more and more researchers are recognizing the importance of statistical analysis as part of the chemometric analysis. So I think it is safe to say that you can include statistical analysis as part of the profiling or chemometric analysis. Okay. Now, I will describe very briefly. As I mentioned, this was discussed in great detail by Dr. Lacerna. I really like the presentation, but just to refresh you, okay, I just quickly describe what goes on in each of these steps in untargeted metabolomics. Okay, so let's start with profiling. Okay, profiling is also known as the differential expression. Okay, so this is quite normally used in clinical medicine or clinical metabolomics, differential expression. Ano yung mga differences ng levels of these metabolites, okay? So between your experimental and control group. Now, this step involves finding metabolites, okay, with statistically significant variation between control and test sample sets. Usually, when you look at the concentration of these metabolites, you don't need to do absolute quantitation, okay? You can use relative quantitation, okay, with relative to a standard or a reference, okay? An internal standard or an external standard, okay? And the goal is actually to compile the metabolite profiles, okay? And the next step is compound identification, which until now it remains to be one of the bottleneck in metabolomics. It's very difficult to identify a metabolite if you don't have a customized or a working library. And unfortunately, this library may come at a steep cost, as mentioned by Dr. Lacerna, but fortunately, we have several databases and machine learning methods that could help us to identify these metabolites in question, okay? So the last step is biological interpretation, and which is the goal of your untargeted metabolomics, okay? When you say biological interpretation, you try to uncover the biological connections and interconnections between the metabolites, and also the result. Also, it provides some insights into the biological mechanism and the processes of diseases, as well as perturbations, biochemical perturbations in the biological system. Okay. So let me go through that very quickly. So let's start with profiling. So mabilis ko lang siyang i-discuss, okay? Because this has been discussed by Dr. Lacerna already, okay? So profiling involves finding metabolites, as I mentioned, with significant variations between your experimental and control. Okay. Now, usually in an untargeted metabolomics workflow, analytical and technical reproducibility is essential. Okay, for to arrive at a stringent data analysis, and these are the keys to a successful experiment. Unfortunately, it comes with a steep price as well. If you want to have a highly reproducible, highly sensitive, and high resolution equipment, you need to invest a lot of money for these instruments. Okay, and luckily we have some of these instruments in the DLSU Central Instrumentation Facility. Okay, we have now the NMR, and it has the highest resolution in the country, and we have QTOF tandem mass spec as well, and both can be used for high resolution, okay, highly reproducible metabolite identification. Okay, now when you say high analytical reproducibility, it means that the data are the direct expression of biological variants. Now, this is very difficult in the clinical setting because of a lot of induced and uninduced variation, and at the same time, inter-individual differences. But there are a lot of approaches to neutralize this variation, and one way is via normalization, which was mentioned by Dr. Lacerna. Okay, and typically metabolite profiling involves 4 steps. Okay, and it is shown here. Okay, sample preparation and data acquisition, spectral pre-processing, feature extraction, and lastly is statistical analysis. Okay, so I will describe them very briefly as we go along. Okay, sample preparation and data acquisition first. This is the first step in profiling. This involves separation and detection of metabolites, and there are a lot of instrumentations you can employ, such as GCMS or LCMS or even ICMS. Now, for untargeted metabolomics, which is the focus of my presentation this morning, both the chromatographic separation and mass spectrometers must have high reproducibility to minimize analytical variation, especially when you're dealing with multitudes of samples coming from populations, okay, or epidemiological samples. Now because untargeted metabolomics aims to comprehensively catalog all the metabolites, it is imperative for the researcher that the analytical technologies perform the following functions as described here. First, it must cover a breed of metabolites with diverse physicochemical properties. So you need to first have some literature survey on the potential metabolites present in your biological sample before deciding which instrument to be used to cover as much of these metabolites in your biological fluids. Okay, so they are very diverse, as I shown you in the previous slide. They have very diverse physicochemical properties. And also, you need to consider instruments that possess large dynamic range to analyze the varying abundance of metabolites. Now, this is very important in clinical metabolomics or biomarker discovery because there are low abundance metabolites with very important biological significance, such as signaling or chemical messengers, such as diacylglycerol. They're normally present in small or minute concentrations in your biological fluid. So if you use an instrument with very small dynamic range, you will not be able to capture these important signaling metabolites. Okay, and at the same time, you also need to cover those metabolites of large abundance. Okay, what are these? These are the metabolites that are involved in energy metabolism, such as ATP, which is always abundant in biological fluids, and also intermediates, okay, that are involved in highly conserved pathways such as glycolysis, okay, and citric acid cycle. They're always high because they are actually central metabolic pathways through which many of the intermediates go through. Okay, so in fact, many of these intermediates are anaplerotic. They give rise to other intermediates that belong in a different pathway. So you see that there are interconnections between these pathways, and this is actually what you want to capture in discovery or untargeted metabolomics. That's why it is important that your platform must have large dynamic range. And this is related to the next bullet, high sensitivity to detect or quantify low abundance metabolites. I'm not going to explain that. I already mentioned that moments ago. And lastly, your instrument must possess high resolution, accurate mass detection, or capability to separate isobaric species. Now, this is true for metabolomics because many metabolites are isobaric. Okay, so in order for you to be able to detect them or identify them, you need a high resolution mass spectrometry. Okay, and usually these high resolution mass spectrometry, you normally that use orbit trap detectors with resolution that reaches as high as 100, okay, 100K. They can perform this high resolution accurate mass detection or HRAM. And most of the mass spectrometers now are equipped with deconvolution programs to allow you to separate isobaric species or various metabolite species that elute at this almost the same retention time. Okay, so and also profiling involves removing background noise. Okay, this is actually one of the culprits in missed metabolite information because some metabolites have very low abundances and they tend to be obscured by these background noises. So you need to be able to separate these background noises by performing baseline correction, peak normalization, and lastly, deconvolution. All these comes very conveniently because there are now commercial softwares that can actually do this very conveniently with minimal human intervention. Okay. So this is an example of the importance of large dynamic range or high sensitivity in metabolomic platforms. Okay, I'm sure that most of you are familiar with citric acid, diba? Citric acid is an organic acid which is an intermediate in the citric acid cycle, or popularly known as the Krebs cycle or the tricarboxylic acid cycle. Now, usually, as I keep on mentioning, the requirements for the choice of analytical platform is that it must possess high sensitivity, technical reproducibility, and large dynamic range, okay, for you to have a successful metabolomic experiment. And this is particularly important in the detection and identification of low abundance metabolites such as citric acid, okay? Now, citric acid has been used. Actually, citric acid has been widely used for the establishment of metastatic cells. Okay, examples are the cells, or these are cells derived from human. I'm trying to recall human tongue squamous cell carcinoma. Okay, and different cells have different metastatic capacity, and through metabolomic screening, okay, through global metabolomic screening and eventually leading to targeted metabolomics, scientists discovered that citric acid could actually identify the low and high metastatic human squamous carcinoma cells. Okay, see, if you have an instrument with large dynamic range, you will be able to cover these very important metabolites that are of minute concentration, but otherwise very important for biological interpretation. So if you don't have a large dynamic range in your instrument, you are going to miss this important information. Imagine if you compare the citric acid across these cancer cell lines, the differences is very, very subtle. So you need to be able to capture this. You need to have a highly sensitive instrument to capture these subtle differences in metabolites, especially if you're doing targeted metabolomics. Now, another example is glutamate and glutamine, okay? Glutamate and glutamine are amino acids, diba? These are amino acids. They're considered essential and semi-essential amino acids. But other than that, glutamine and glutamate exchange is important for energy provision in certain metabolically active cells, such as kidney cells, in the event of low energy status. They could actually use glutamate and glutamine exchange pathway to extract energy from this. Okay, therefore, it is important to profile them. Okay, unfortunately, okay, glutamate and glutamine have very close structures. Okay, and they would come out at almost the same retention time, and this particularly becomes difficult if you don't have a deconvolution software. You're going to miss this important information. Okay, but if you have a high resolution analyzer such as Orbitrap analyzer here, you can practically separate these two, okay, metabolites, and you can effectively identify them with high level of confidence. If you have a low resolution analyzer such as QTOF, actually QTOF, personally medyo mataas pa to. The resolution could reach up to 20,000. But if you're dealing with metabolites such as glutamate and glutamine, QTOF may not be a wise choice as an analyzer to detect these metabolites. Okay, this is something to think about for the choice of platform for your metabolomics work. Okay, and lastly, feature extraction. So again, I'm very lucky. Dr. Lacerna did a great presentation on this. Okay, as if you recall, metabolomics data are highly multidimensional data. Okay, sa isang metabolite pa lang, you can actually generate a lot of information, okay, such as retention time, mass to charge ratio from their extracted ion chromatogram or EIC. You have the intensity, you have the peak area, and so on. Let alone if you're dealing with thousands of metabolites and multitudes of samples. So your by nature metabolomics data is highly multidimensional. And these parameters that I mentioned a while ago are what you call the features that actually characterize your metabolites. They call that at this stage of profiling, you don't know the identity of your metabolites. Okay, the identity of metabolites, okay, can be, or the metabolites can be identified through these features. Okay, so these allow you to locate and quantify your metabolites, either relatively or relative or absolute quantification. And feature extraction, again, this comes very convenient for the researchers nowadays because there are many softwares that are equipped with tick-based algorithms. They can actually do feature extraction for you, okay, simultaneously for all the potential metabolites. Okay, and kanina, Dr. Lacerna mentioned of the spectral binning. Okay, so this is part of the feature extraction as well, wherein related ions, okay, that are indicative of the extracted ion chromatographic peak, okay, are identified and they are grouped. Okay, so this is important. Okay, the spectral binning. Okay, so this is an example of feature extraction from an extracted ion chromatogram here. I am not entirely sure what metabolite this is because at this stage we do not know yet. Okay, so that is why we need to do feature extraction beforehand. Okay, so this is the extracted ion chromatogram here. So, and then following mass spectrometry, okay, following separation, you do mass spectrometry. and then you collapse these into their mass fingerprint. The mass fingerprint then is grouped according to the ions, either singly charged, multiply charged, okay? And you do the spectral binning, okay, of these extracted ion chromatogram. Okay, so these feature extraction allow you to organize your data that is now ready for subsequent analysis. Okay, now it is very important to know that spectral binning is actually one of the acceptable data for high-level functional interpretation. So if you do this manually, it's going to take a lot of time, but there are many softwares now that can do spectral binning, which is a lot more convenient. Okay. Okay, and lastly, the statistical analysis. And again, happy that Dr. Lacerna mentioned this statistical analysis. And traditionally, we do two types of statistical analysis, the univariate and multivariate. Perhaps the more familiar to you is the univariate method, such as t-test and ANOVA test. They're commonly used. However, one of the pitfalls of this univariate method is that they don't take into account the presence of interactions between the different metabolic features as if they occur independently. Okay, so this is actually not underscored in univariate methods. In fact, univariate methods is normally applied in targeted metabolomics. Okay, now for discovery metabolomics, the most useful is the multivariate method. Again, I enjoyed Dr. Lacerna's discussion on this, very clear, detailed, rich in information. So you can do supervised multivariate analysis, such as principal component analysis, or you can actually label your features according to classes and do supervised. Sorry, this is supposed to be, PCA is unsupervised while PLSDA is supposed to be supervised, or partial least squares determinant analysis. Okay, so as Dr. Lacerna mentioned, this allows us to, because your metabolomics data are highly multidimensional, so many parameters, so many data, so you can project them into fewer components. So you can do this beforehand to look at the differential expression of these metabolites between control and experimental group. Okay, and this is routinely done before metabolite identification. Because if you skip this step and you do metabolite identification, and after that you realize that there's no difference between your control group and disease group, in this case you have wild type and mutant, then metabolite identification will be practically pointless. That's why statistical analysis, I emphasize multivariate methods, is a very crucial step, okay, in the differential expression analysis. This gives you the proof of concept so that you can proceed to the metabolite identification and eventually do high-level functional interpretation such as pathway analysis and metabolite set enrichment analysis. Okay, so metabolite identification is our next topic. Okay, so again, I'm glad that this was covered by Dr. Lacerna. So this is actually the bottleneck on untargeted metabolomics research. Okay, even my group has had difficulties in identifying metabolites because we don't have a library. We don't have a customized library to identify these metabolites, and we mainly rely on databases. And in fact, database search forms one of the important platforms for metabolite identification. Okay, so for MS database searching, you could use Metlin or MZ Cloud. Okay, however, it lacks sufficient specificity for identity confirmation. When you want to do validation, the MS database searching may not be as useful, okay, as it sounds. But that's the first approach usually, especially if you don't have a library, which is quite costly. So you could use this mass spectrometry database searching, and then. Now, if you have tandem mass spectrometry, in which case DLSU-CF has it, then you can do tandem mass spectral library matching. Okay. Now, these library matching employs fragmented molecular ions. Okay, that can be compared against the tandem mass spectral libraries or electron impact libraries. Okay, and along with your retention time, okay, this can provide the high level of confidence. Okay, so now this is an example of a library. Okay, so this is a commercial library, by the way. It's already comes with your, for example, with your QTOF tandem mass spec, especially if you want to dedicate that instrument for metabolite or metabolomics work, you need to have a dedicated library for your targeted metabolites. And this comes with a steep price as well. Okay, so, but it's very convenient because you don't have to use those databases anymore. So right there, you can customize it, okay, depending on the known metabolites from the previous literatures, and you can identify these metabolites with high confidence. But oftentimes, there will still be metabolites that will be left unidentified, even if you use these costly libraries. Okay, so that is why you need to do other approach. Okay, especially if you're not able to identify a particular metabolite. What can be done? Okay, then you will have to rely on your knowledge on your mass spectrometry, okay, or possibly in your NMR spectroscopy. So this requires high level skills. Okay, the de novo interpretation, where you reconstruct a chemical structure based on fragmentation data without prior knowledge on them. Okay, and also you can do structural correlation. Usually, this is an in silico method, comparing your experimental mass spectra, okay, from that of the in silico generated mass spectra of a particular metabolite. Okay, but this is very useful, okay, to structural correlation, and there are a number of publicly available databases that can be used for this structural correlation in the absence of these commercial softwares. Okay, one such commercial software or database is what you call the My Compound ID or MCID. Now, this is a web-based tool for metabolite identification based on integrated mass spectrometry or tandem mass spectrometry. Okay, sorry about the annotation. Now, the MCID library contains a predicted tandem mass spectra. Take note, this is in silico generated tandem mass spectra of over or close to 400,000 known and potentially existing human metabolites. Okay, and the current MCID library now includes over 8,000 endogenous human metabolites that are curated in the Human Metabolome database, and almost 400,000 predicted metabolites in EML. I forgot what EML stands for, evidence-based metabolome library, or EML, which is based on one metabolic reaction only. Okay, that's why between HMDB and EML, HMDB still proves to be more useful in metabolite identification for discovery metabolomics. And the last step is functional interpretation. So I'm going to go through this quickly because this was already discussed in the previous presentation. Now, in functional interpretation, you can use a lot of public software such as MetaboAnalyst. MetaboAnalyst could actually give you provide you interactive graphical displays. Para siyang Google Map based graphical map. Shows you the identified metabolites and position them on pathways that help reduce their function. Okay, so it is again goes back to the HMDB. One of the databases used by MetaboAnalyst is actually Human Metabolome Database, or HMDB. But other databases are also used, such as EML and also Metacycli. Group of metabolites, okay, now in functional interpretation, the group of metabolites that are related to the same biological processes are placed in unique metabolic pathways following stringent statistical categorization. Okay, so sometimes the software will actually set the settings by default, or you could actually even more stringent, especially if you want to do clinical validation later. You have to be quite stringent with this step. Okay, wherein you place certain metabolites in biological pathways and eventually underscore them as overrepresented or significantly dysregulated. Okay, and the purpose of this functional interpretation is to identify connections between metabolites. Okay, and that is the goal of discovery metabolomics, right? You want to find connections and interconnection between this metabolite, because they can actually provide you insights into these disease mechanisms. And eventually you want to use this as biomarker for biomarker discovery. And when validated, okay, clinically, they can be applied in the clinical setting for diagnosis of diseases and also for assessing response to treatments or as prognostic markers. Okay, now high-level functional interpretation usually uses these databases as outlined by Dr. Lacerna. Okay, the KEG or the Kyoto Encyclopedia of Genes and Genomes, the Meta-SciC, okay, the Small Molecule Pathway Database, SMDB, the Wiki Pathways also is quite useful, but the number of pathways, okay, that are cataloged or curated in Wiki Pathways is not that much compared to KAGG, okay? And lastly, if you're dealing with plant metabolites, you can also use PMN or plant size C. And this is actually a multi-species pathway database for plant metabolomics, okay, such as rice. Now, MetaboAnalyst, okay, came around some years ago, and there is now, I don't know the newest version, I think version 5. It now integrates high-level omics analysis, where you can integrate data, okay, from your genomics, transcriptomics, and proteomics, along with your metabolomics, and you can obtain high-level functional description of your metabolomics work, okay? Now, in comparison with other programs such as XCMS, Galaxy, your metabolomics, as I mentioned by Dr. Lacena, it's like a one-stop shop. You can do spectral pre-processing, you can do normalization, you can do statistical analysis, okay, both supervised and unsupervised and supervised. And I think one of the magnificent applications of these metaboanalysts is the high-level functional interpretation, such as pathway analysis and metabolite set engagement analysis, and also pathway topology analysis, which identifies the centrality of your metabolites, okay, in a given pathway. Okay, so this is an example of metabolomics data interpretation. It made use of a commercial software. This is not generated by MetaboAnalyst, but this is highly intuitive because it actually project your data on a network or systems context, their connections, okay, and also the pathways they are involved. Okay, and you can also do heat map analysis so that you can actually gain insights into the relative, okay, expression of these metabolites, okay, using heat maps. Okay, now heat maps is not exclusive in metabolomics. It's been applied for many years in genomics, transcriptomics, and proteomics, but fairly recently, it is now widely applied in metabolomics as well. Okay. So I mentioned a while ago that the focus of this presentation is how can we employ metabolomics, okay, especially basic research in metabolomics in the clinical setting. Now, if I may be honest, this is actually a long way to go, okay, application of metabolomics sa clinical setting. It is because you need to validate, okay, metabolic markers, okay, in a large population because before you can actually apply it in the clinical setting. But that is highly possible, okay, in metabolomics work, but it's going to be really ambitious. But a lot of research groups now are working towards translational medicine and personalized medicine, wherein they employ metabolomics data in understanding disease mechanisms, okay, which later on can be validated for personalized medicine, okay. Now, so I would say one of the most widely used application of metabolomics is biomarker discovery, okay. I'm sure you are all familiar with biomarkers, okay? And you know what biomarkers is. By definition, biomarkers are a characteristic that is biochemical characteristic that is objectively measured and evaluated as an indicator of normal biological process or a pathophysiological or pathogenic process. And very importantly, the responses of an organism such as humans to pharmacological treatments and other environmental factors or any therapeutic or nutritional intervention. Okay. In fact, the biomarkers form the cornerstone of the treatment individualization in personal medicine. That is the goal. You need to individualize, okay, the biomarkers for the diagnostic of diseases and also assessing response to various treatments or therapeutic intervention. Okay. Now, however, okay, the application of metabolomics, okay, in the clinical setting suffers from multiple patient-specific factors. Okay, it can be these multiple patient-specific factors may be influenced by the metabolome and but you can control this, okay, variation using a carefully designed research study to minimize the variation. However, there are patient-specific factors that will affect, okay, your metabolite identification and biological interpretation. So you have the inter-individual variation. Okay, for example, the demographics of your experimental group or your cohort, such as gender, age, body weight, their comorbidities, their concomitant medications, all these can actually influence the metabolome. Good thing now that we have some machine learning methods and algorithms that can actually neutralize these variations. Okay. Now, I think it is important in the clinical medicine when you apply metabolomics in the clinical setting is that the biomarkers could be dynamic or could be static biomarkers or static prognostic biomarkers. So what's the difference between dynamic and static prognostic biomarkers? Okay, so when you say dynamic markers, biomarkers, they describe the disease progression and they are associated with the disease response. Okay, so over time, they can vary. So there will be temporal differences in these biomarkers, and you need to be able to capture them over time. So this is what you call longitudinal metabolomic profiling. Okay. Now, on the other hand, the static prognostic markers, okay, these are usually used for prognostic purposes, and the aim is to predict clinical response or a dynamic biomarker thereof. Okay, so usually you start with a static biomarker discovery, and then you can proceed to dynamic biomarker discovery. Okay, now examples of dynamic biomarker discovery would be response to treatments or how does chemotherapeutic intervention influences certain metabolites over time. Okay, so static prognostic biomarkers, okay, examples of this is biomarkers that could actually diagnose, okay, with high confidence certain diseases such as cancer. Okay, and recently colleagues of mine from the University College of Dublin patented metabolite biomarkers that could actually lead to high-level diagnosis of certain types of prostate cancer among the Irish population. Now, why do we need metabolomics? Okay, why do we need this in the clinical setting? Well, we have a lot of clinical biomarkers for the diagnosis of diseases, but these biomarkers, okay, they suffer from low sensitivity at times and or lack of specificity. Okay, majority of these biomarkers have been developed or identified decades ago, and however, we still need other biomarkers or indicators because many of these biomarkers are not very sensitive in disease diagnosis, okay, or even as a prognostic marker. So I'll give an example that was provided by Dr. Acerna. The creatinine and urea are traditionally used as a biomarker for kidney disorders. It's traditionally used in the clinical practice as markers for clinical kidney disorders. However, these two biomarkers, they are sometimes not very sensitive in detecting certain renal disorders, especially chronic renal disorders. Therefore, we need innovative metabolomics work, okay, which comprises molecular intermediates, okay, in the pathway, and also end products resulting from different cellular and physiological process. So this is the advantages of metabolomics, because they could actually reflect dysregulation in the cellular physiology and pathophysiology relating to a disease. Okay. Now, more on precision medicine. Okay, I think you are well aware that most of the metabolomics applied in the clinical setting start with a proof of concept study. Okay. For example, in clinical metabolomics, biomarker discovery, ultimately, you generate a quantitative data that are chemically and biologically interpretable, and it's of great importance in disease mechanism. Okay. Now, however, okay, one of the weaknesses of this is individuals have inter-individual variation. Okay, so therefore you need large number of samples, okay, from your population cohorts to arrive at a biomarker, metabolite biomarker that can eventually be used or validated and apply in the clinical setting. Okay, now, in fact, a large number of clinical metabolomics employ this, okay, case control studies. Okay, and these case control studies are aimed at identifying differences between metabolite signatures, okay, of group of patients such as healthy and disease. Now, however, such categorization are often inappropriate or oversimplification, especially if the treatment individualization biomarkers, okay, are inherently dynamic processes. Okay, so especially if you're looking at metabolites that are by nature very dynamic or fluctuating. Okay, so that's why you need to employ a very carefully designed carefully designed research when you want to employ metabolomics in the clinical setting. Okay, and as I mentioned, this suffers clinical metabolomics suffers from serious intra-individual variability, and this results in a highly convoluted intra and inter-individual variation or metabolic signatures. Within the same individual, okay, there would be dynamic changes in the metabolites. Okay, that's why it's very difficult to capture them using static approach. So you need to employ both static and dynamic, okay, approach, okay, in the clinical metabolomics. So now, eventually, okay, you will arrive at metabolomic profile. Okay, that's actually one of the goals, okay, as outlined in the workflow in metabolomics. Based on this metabolomic profile, you can actually generate a model, okay, emerging from your high-level functional interpretation, such as pathway analysis, metabolite set enrichment analysis, and pathway topology analysis. And eventually, as Dr. Lacerna mentioned, you need to be able to validate this in larger patient cohorts so that eventually it can reach the clinical bench, okay, such as for the application for treatment individualization biomarker or prognostic biomarkers, such as what is known as the personalized or precision medicine. Okay. Now, however, as I mentioned, there are still a lot of things, okay, that should be done, okay, in the field of clinical metabolomics so that eventually it reaches the clinical setting. Okay. But over the past couple of years, there have been significant advancement in analytical instrumentation and systems biology that allow that actually propel these clinical metabolomics, leading to applications in the clinical setting. Okay. Now, these are some of the opportunities and challenges in metabolomics aside from understanding disease pathophysiology. Okay, you could also use metabolites, signatures as potential biomarkers of nutritional deficiency, and that is actually one of the goals of my research group. We use biological fluids to underscore metabolite changes in metabolites in biological fluids such as serum plasma and breast milk from Filipino lactating women. Then, very interestingly, you can classify these individuals into their specific metabotypes. Okay, now this is good for nutritional surveillance. Okay, and can be combined with your genomics data. So if you have certain genotypes that could potentially lead to a dysfunction in the metabolite makeup on an organism, then you can actually do metabotyping of individuals or population. And lastly, assessment of metabolic changes following nutritional intervention or modification, and integrative approaches, okay, in understanding disease pathophysiology that requires genomics, transcriptomics, proteomics, and metabolomic data. So it's actually a multidisciplinary approach to be able to arrive at a mature and highly functional data, okay, that will describe your disease mechanism. Okay. Now, in the next few slides, I'm quite close to conclusion. In the next few slides, I will just share to you what we have been doing, okay, as part of my metabolomics initiative in De La Salle University. So this is actually in collaboration with the Food and Nutrition Research Institute of the Department of Science and Technology. As you know, FNRI is the premier arm of the government in food and nutrition research. Been lucky to collaborate with them in this study, and they provided the precious breast milk samples from the Filipino lactating women who participate in the National Nutrition Survey. So, to my knowledge, our group is the first one to characterize the comprehensive metabolome of breast milk using both NMR and mass spectrometry approaches. So this shows you representative total ion chromatogram from the GCMS analysis of the breast milk samples obtained from the FNRI. So these are the Filipino lactating women, okay? So we identified several metabolites using GCMS, and majority of them are lipid metabolites, such as glycerol, caproic acid, capric acid, lauric acids, and so on. And we also identified other metabolites, such as hormone intermediates. This is actually a work of my master's student who has now graduated. Okay, Gerald. Okay, he also do NMR analysis of the breast milk. Okay, so we actually grabbed the opportunity to use the NMR over in the LSU SCIF, a very powerful NMR, and in collaboration with UCD Conway Institute in Ireland, we were able to probe a lot of metabolites, okay, using the NMR. So, for example, we identified certain amino acids, okay, organic acids, okay, derivatives of amino acids, okay, and also lipid metabolites such as choline, phosphocholine, and their intermediates, okay. And we were able to conduct high-level functional interpretation using MetaboAnalyst. So MetaboAnalyst is a publicly available program that it's highly cited by researchers, and it's been peer-reviewed. So do not shy away from using this because it's very, very useful and very beneficial for startup researchers on metabolomics. Okay, so this is actually the metabolite pathway network overview as the result of the metabolite set enrichment analysis obtained using the MetaboAnalyst software. Okay, as you can see, there are nodes here that were identified as overrepresented, and as expected, most of them relate to lipid metabolism, such as bioacid biosynthesis, and also amino acid metabolism, and also beta oxidation of very, very long chain fatty acids. Okay, and this is the graphical overview of that breast milk metabolome, highlighting the centrality of those metabolites that we identified. Okay, so each of these nodes, okay, corresponds to the pathway impacts, as mentioned by Dr. Lacerna, of the match metabolites of a given metabolic pathway. Not only it indicates a significantly dysregulated pathway, but also the centrality of these metabolites in this pathway. So for functional interpretation purposes, you could use pathway topology analysis in MetaboAnalyst to assess the centrality of your metabolites. Okay. And also, when you say centrality, the significance of these metabolites in a particular pathway. Usually, these metabolites serve as intermediates, okay, for the synthesis of other important metabolites in a given pathway, and that highlights their functional importance in a given pathway. So this can be done in MetaboAnalyst via pathway topology analysis. So this is the summary of my presentation. So metabolomics, let me reiterate that metabolomics, its main goal is to screen small molecules that we call metabolites in complex biological samples or biological fluids. It provides a snapshot of the metabolism. This is also called the fingerprint, biochemical fingerprint of an organism. And one of the advantages is that this can reflect the physiological state of the organism, understand the, or reveal information on disease phenotypes. And among the omics approaches, I highlighted metabolomics being very sensitive to various environmental and physiological stimuli. Therefore, many researchers now are recognizing the importance of metabolomics, serving as the ultimate phenotype of organisms, including humans. In clinical metabolomics, which aims to identify these small molecules present in patient-derived samples, such as blood, serum, okay, serum, plasma, urine, sweat, saliva, breast milk. Okay, they've been attracting attention to support discovery of novel disease biomarkers. However, it remains to be a bottleneck, okay, in its application in the clinical setting. In fact, consensus in best practices for the integration of metabolomics in the clinical practice remains to be warranted or are still lacking at this stage. Okay, but as I mentioned, in the years to come, there are maraming advancement, not only in analytical instrumentation, but also in systems biology that could actually address this limitation of application of metabolomics in the clinical scene. Lastly, I'd like to thank everybody who attended this webinar. It's very well attended. I'm quite nervous presenting a while ago, realizing that there's over 100 attendees. So congratulations to the organizers, the DLSU CIF, PSHRD DOST, Dr. Camacho, Dr. Lacerna. Thank you for inviting me. I'm very delighted. Although I must say I'm not yet established in metabolomics, I'm a very early researcher. I'm at a very early career stage as a metabolomics researcher. So at this stage, I don't consider myself as an established person or established metabolomics scientist, but I'm really enjoying investigating a lot of disease phenotypes using metabolomics platform. So maybe over the years, with the help of my colleagues, especially Dr. Lacerna, we will be able to establish metabolomics facility in the university, and who knows, it could be a resource center here in the country, especially that metabolomics is still in the incipient stages of development in the Philippines. Thank you again and have a nice day. I'll be delighted to answer questions during the open forum. Okay, let's go back.
Thank you, Dr. Sumaya, for delivering a great talk on metabolomics in the clinical setting. Your discussion was very helpful in imbibing and interjecting the concepts which were introduced earlier by Dr. Lacerna. So the alignment and the cumulative impact of both your talks are outstanding, and we really enjoyed listening and learning these concepts. It's past 12 p.m., but hopefully we can still join you over lunch. To recap, Dr. Sumayo gave a short overview on metabolomics, which was discussed in detail during the last two sessions of the webinar series by Dr. Lacerna. He also discussed two approaches on metabolomic tools and strategies, including untargeted or discovery metabolomics, which involves unbiased screening of metabolites in a biological sample, comparison of patterns or profiles of metabolites among different sample groups, and more. Second is the targeted metabolomics, which focuses on the validation of selected metabolites as well as utilizes a large number of samples. It often relates to a specific metabolic pathway. You also mentioned the typical workflow of untargeted metabolomics, similar to Doc Karen's discussion earlier, relating it to the clinical application. Although the application of metabolomics in the clinical setting has a long way to go, it is highly possible. The limitations of MS techniques in some applications were also emphasized. Clearly, it is very important to align your research objectives to the equipment, software, or technology in general that you have access to avoid issues later on that may have serious repercussions, especially for funded projects. Finally, the centrality of metabolites in their breast milk metabolome of Filipino lactating women study via pathway topology analysis was also discussed by our guest speaker. Again, these are all too much information to handle in one sitting, and if you wish to go back to the discussion, kindly check out our live section for the under the DLSU Center Instrumentation Facility Facebook page. And so thank you so much, Dr. Karen and Dr. Sumayo, for your talk. At this point in time, we would like to begin reading and responding to some of the questions that you have posted. So may I invite Dr. Karen and Dr. Asarod to open their cameras and microphones for the Q&A session. Hi, Sir Rod and Dr. Karen. How are you? Yeah.
Hi, Sir
Hello.
Rod. Great talk po.
I'm confident that Dr.
Super
Lacerna is
happy.
here. Merong mag-rescue sa akin.
Okay.
Kaya niyo po yan. So, we're now actually waiting for questions, guys. So, from our audience, kindly input your questions if you have any. So, yung mga taga-Facebook, yung mga nakatutok sa Facebook, kindly enter the questions as well via the comment section. So, while waiting, pwede po muna tayo magsikahan. And so how was the series, and Dr. Karen? I mean, how was the experience of talking about metabolomics for the past 3 sessions?
Super. Hanggang ngayon, medyo kinakabahan pa ako, nire-reviews pa ako. And yeah, it was really fun. Especially I get to share this webinar with really great presentations as well from Doc Fe, Doc Mel, and Sir Rod, and super nag-enjoy ako. So thank you po.
Thank you, Doc Karen. So, sobrang dami talaga namin natunan. Kailangan, kahit kami sa CIF, kailangan din namin talagang balikan yung mga recordings para ma-absorb namin lahat ng information. Thank you po so much again. And Sir Rod, kamusta naman po yung experience natin?
Well, just like Dr. Lacerna, I'm equally nervous. Siguro mas yung nervous ko mas grabe kasi you have such a large audience. Dr. Lacerna has been talking for the past few weeks. So medyo siguro gamay niya na yung mga audience. But in my case, I think I consider this as one of the largest audience before me presenting a metabolomics work. And thank you, Chris, kasi you helped me to calm my nerves by including me in your quiz. And some trivia on the course. Sabi ko nga, nakabanggaan ko sila. Literally, isa sa mga bars sa Dublin. So that actually calmed my nerves. And hopefully, that will help me in answering the questions of our dear audience.
Kaya niya yan, sir. And salamat po din sa pag-accept sa aming invitation. Okay. Sana all. Nakabangga yung the course.
Oo nga
eh.
Talaga. Okay.
Actually, hinihintay ko i-acknowledge mo yung Westlife eh.
Ay, oo pala, no, nakalimutan ko rin.
Actually,
Next time,
naisip
sir.
ko rin yun eh,
Next
Westlife.
time. Next
Oo.
time. Sige po. Ayan po, actually, we have a question already. So let's read the question from actually your previous advisee, Gerald Haen. So thanks for the talk, Dr. Sumaya. With regards to the metabolome of a specific biological sample, what current strategies are utilized to distinguish the endogenous metabolome from the exogenous metabolome?
Thank you, Gerald. I think I should mention Gerald is my thesis advisee. He successfully graduated MS. In fact, I presented his work on breast milk metabolomics earlier. Sa kanyang work yon. Well, this is actually one of the difficulties in metabolomics because it will capture both, okay, the xenobiotics and also the endogenously obtained metabolites. Okay. I suppose that will differentiate them would be the databases for the identification of metabolome, because these databases are usually designed to identify endogenously derived metabolites. Okay. There are, I think, I'm not entirely sure, maybe we can ask Dr. Lacerna, there might be some databases that could identify or target specifically xenobiotics. Okay, but the difficulty here is that many of these xenobiotics would somehow uh, uh, obscure, okay, certain metabolites, okay, that are endogenously derived, such as, for example, yung mga essential amino acids and non-essential amino acids. Okay, some amino acids now, they can be categorized as xenobiotic because they cannot be synthesized by the body. But, merong there are very minute differences in certain endogenously derived metabolites and some xenometabolites, and this will actually present difficulty in terms of metabolite identification. So that's why if you encounter this difficulty, sometimes you need to do de novo metabolite identification to rule out structural differences between the two. Because when you take in these xenobiotics, they will be metabolized by your body, by your cells, especially by the liver. And this will actually generate a lot of intermediates, which can be falsely identified as endogenously derived metabolites. But I don't have that huge experience on detecting these metabolites, but I think Dr. Lacerna has, kasi si Dr. Lacerna very comprehensive experience on metabolomics. So I think the analytical instrumentation and the database for metabolite identification can rule out the differences between the two.
Okay.
Okay.
I just wanted to add dun sa answer ni Sir Rod. What Sir Rod has said is really correct. Currently, if you're referring to exogenous metabolome in the sense that these can be endogenous metabolome that are actually derived from exogenous sources, yes, mahirap siyang i-differentiate. Everything gets all mixed up if you look at the metabolome profile of an individual. But if we're looking at xenobiotic metabolites, that means certain pollutants, drugs, or whatever xenobiotic agents and their metabolism. Yes, they can be identified using de novo approaches, making use of, for example, in one of the papers that I have presented dun sa first na talk, we made use of high resolution LCMS analysis, wherein we identified the different metabolites that are produced from the intake of earthworms of triphenyl phosphate or tributyl phosphate. I forgot which pollutant. But yes, these are approaches that you can use to identify exogenous metabolome. So I hope that could help to answer your question regarding exogenous metabolome characterization.
Right. Thank you, Dr. and Sarot, for your answers. So hopefully those were enough to satisfy Mr. Gerald, Mr. Haen. Okay. Thank you so much. Moving on to the next question. thank you to all speakers. Can you please send us the post-evaluation link? Yes, we will do that a bit later after the open forum. So I'll now be reading one question from the Facebook Live chat box. This is from Angelique Tavera. Angie says, "Hello, Dr. Sumayaw. Angelique Tavera from the BCRU. I hope you remember me. Thank you for the talk. This was very informative on my part as my research is starting to focus on medical entomology following metabolomics approach." So again, medical entomology following metabolomics approach. While I understand your examples are on humans, would you happen to know, sir, if the same workflow would apply for insect research, specifically on pest management? So that was the question from Miss Angelique Tavera. Okay. So you're on mute po, Sir Rod.
Sorry about that. Yes, Angelique. Hi, Angelique. Thank you for the question. Of course, I remember you very clearly. And I'm very interested with your research. You're studying insects with Dr. Hanairo. Yes, indeed. You can actually employ the same workflows that we described, Dr. Lacerna and I, for insects. In fact, merong databases for insects. Okay, sa Metabo Analyst, maraming mga species that you can choose, not only for humans, but insects as well and other organisms. Yes, definitely you can do all those chemometric analysis, statistic analysis, including high-level functional analysis such as pathway and metabolite set enrichment for insects. Okay, so halos wala akong nakikitang difference when it comes to treatment of data, but you need to be able to choose the database that is intended only for that specific organism.
Great. Thank you, sir. Dr. Karen, do you want to chime in on the question?
Okay. So as Sir Rod has mentioned, yes, current databases, pathway databases such as your KGG, Metapsych, the Metabo Analyst, they have different model organisms na available yung data in terms of metabolic pathway. In terms of insect, I think mainly Drosophila. But definitely, as Sir Rod has mentioned, you can apply the same metabolomics workflow and pathway analyses in your own research.
Thank you, Dr. Karen. I hope these answers were enough to satisfy you, Angie. Thank you so much for the question. Next question would be from Ms. Marilyn Miranda. Good afternoon. Using Metabo Analyst, can it also analyze LC-GCMS data? Or it needs to be LC/GCMS-MS. I think in XCMS, it needs to be an LC-GCMS. So that was a question from the Zoom chat box from Ms. Marilyn Miranda. So does anyone want to answer?
Okay. Can also analyze LCGCMS data. Okay. Actually, in Metabo Analyst, it is mainly LCMS or GCMS data. Kasi most of the time naman, ang ginagamit lang nila is yung TOF-MS or high resolution MS scans for the analysis. If you're talking about molecular networking, I'm not sure whether Metabo Analyst has functionalities for that, but in terms of molecular networking using yung GNPS or some other web-based platforms, doon pumapasok yung MS data. So yun. So it's mainly LCMS or GCMS data, high resolution, for purposes of subsequent identification, yung mga putative identification.
Anything to add, Dr. Sumaya?
I think I will not add further. I completely agree with Karen. Okay, so you can actually use it doesn't have to be tandem aspect. Okay, so kaya lang in terms of functional interpretation, possibly the scope of your metabolome may not be captured completely. Okay, if you use low resolution analytical instrument. And I think it is important to note that Uh, Not one analytical instrument can comprehensively cover or capture all the panel or inventory of metabolites in an organism. You actually you need to use different approaches, mass spectrometry and NMR approaches. Okay, so in fact, researchers these days they actually do both mass spectrometry and NMR. Okay, especially for NMR, if you are looking at high abundance metabolites, and NMR will be very useful. Okay, so to complement your mass spectrometry analysis. And also, it is important to note that you can actually capture the same metabolites using mass spectrometry and NMR. Okay, so it's good to complement your metabolite profiling and identification with with this instrument, and you don't just rely on just one, and you need to have a proof of concept as well. Okay, I'm sure that there are literature uh, sources that will provide you some proof of concept on the potential metabolites you could possibly see in your biological fluid. So that will actually aid you in choosing what platform you need to use. It's like possibly databases and softwares that can possibly use. Metabolomics work require a lot of planning. So parang sabi ko nga sa mga students ko, you don't just wake up one morning and decide to do metabolomics. And Dr. Lacerna is in a very good position to do this kasi he has so many years doing metabolomics work, and now she's now in the Philippines doing this. So it would be very challenging, but with her help, okay, I think it's going to be very possible for us to be in a good position in metabolomics study in the country.
Thank you so much, sir, for the insights. Dami talagang dagdag. Okay? And yun nga, again, I'd like to emphasize we're really lucky to have Dr. Karen here in the Philippines. So hopefully moving forward, we can do a lot of collaborations and researches, not only within LaSalle, but also with other universities as well, and other organizations, government, etc. Okay? So for the next two questions, I'll be reading. Siguro we can just choose at least one of you po to answer in the interest of time. So for this one, for the next question, it would be Dr. Sumayaw. Hi po, Dr. Sumayaw. This is from Abigail Ruth. Mutations in an enzyme can affect its activity. Could the change in enzyme activity be better observed or studied in metabolomics? Thank you. Sir, you are muted.
Okay. Sorry, I kept forgetting unmuting my microphone. Thank you, Abigail, for that very interesting question. And that's very difficult to answer. Kasi if you recall, isa sa mga slides ko, one of the researchers performed PCA analysis comparing mutant and wild type. Okay, so by altering the gene, okay, you can actually look at the dysregulation, dysmetabolites between control and wild type. However, that's actually just one prospect. If you see the changes in the metabolites, you do the profiling and functional interpretation, you can actually go back, okay, and identify what these enzymes could be potentially affected, okay, by this dysregulation in metabolites. But this is going to be a tremendous task kasi the differences or changes in metabolites is not always a consequence of a mutation in an enzyme. Okay, that is just a possible consequence. But there could be a lot of factors that contribute to these metabolomic changes. Okay, as I mentioned, there are environmental factors and physiological factors. Okay, I think among these factors, the environmental and physiological factors would actually contribute or influence the metabolomic changes in an individual or an organism. But if you want to look at the mutations in an enzyme, okay, I think that's possible. You have to work backwards. Okay, for example, you found out that this particular pathway is dysregulated because these metabolites have been highlighted by the metaboanalyst and any other software. You go back to that pathway and then you can examine each of these enzymes. But that's a lot of work because you do not know which enzymes are affected. So maybe you can narrow it down by looking at enzymes that are involved in rate limiting step of that particular pathway. But you don't look at each of the enzyme because that I imagine that would be a lot of work. Okay, so you look at critical enzymes maybe, and then look at the mutation. But you have to have a goal. Why would you look at the mutation? Okay, traditionally that is not the goal of metabolomics. But if you have other objectives, I think you need to narrow down your objectives. Okay, and you need to know. You really need to know why you will need a metabolomics if eventually you want to find out the mutations in the particular enzyme. Okay, so that will depend on the objective of your study. Because maybe if you want to look at the mutations in a particular enzyme, maybe you don't need metabolomics. Okay? Kasi nga, ang daming work nun. Okay? So, maybe you can do targeted metabolomics. Maybe Dr. Lacerna will agree this. When you do targeted metabolomics, actually you're narrowing the scope, okay, of your objective. So that way it's easier, it's going to be more convenient to look at the enzymes individually. But I cannot imagine doing this in a discovery metabolomics. Okay, baka mahirap pa, but it's possible. I'm not saying it's not possible, but it is possible depending on your objective or your goal.
I do agree with Sir Rod on this. That's the importance of establishing right away at the start kung ano ba talaga yung objective mo for your study. Because in some cases it is really more practical and more in some kumbaga cost saving, time saving to take yung targeted metabolomics approach if you're looking at particular yung gene yung function of certain genes, or if you're looking at specific questions in terms of mutation. So definitely you can consider using the targeted approach of metabolomics for specific questions.
All right, thank you so much, Lokaren and Sarot, for the elaborate answers to Miss Abigail Ruth's question. So hopefully, those answered your question, Miss Abigail. And for the last question for this webinar series, we have a question from Miss Annabel Flores. Can NMR alone be used in omics? Actually, this was answered before, but maybe we'll have more insights. Can NMR alone be used in omics, or shall it be in tandem with other equipment like LCMS or GCMS? I understand NMR is a bit new, unlike with GC, for example, which already has established library. So maybe we can emphasize on the answers earlier. Go ahead,
Okay.
Lokaren.
So as Sir Rod has mentioned earlier in the open forum, there's no one instrument platform that can cover the whole metabolome. And so usually you make use of complementary platforms. In the case of NMR, yes, you can make use of it for a particular study if you only want to characterize your metabolic profile. Pero if you want comprehensivity, hindi niya ma-address yon kasi as Sir Rod has mentioned several times, there are a lot of these very important metabolites that are present in very low concentration. So, hindi siya, posible na hindi siya makover ng NMR because of sensitivity issues. One thing that has worked for me in most of the applications, and I think this is something that I usually observe, I'll get more of the primary metabolism changes with the NMR, and then I'll get more specific changes that are related to secondary metabolism or immunomodulation in the MS side. So makita mo yung complementary information that these different instrumentation can provide. But yes, it can be used for metabolomic studies, but it depends kung gaano ba comprehensive yung gusto mong makita. Um, in terms of databases, actually NMR is well established. You can find this paper by Dr. Jeremy Nicholson. He has a characterization of the metabolome of plasma, and you can see from his list, like almost all primary metabolites can actually be captured using NMR. But again, ang limitation is yung sensitivity sometimes yun.
Right, thank you so much, Doc Karen, for the answer. I don't think we have more time to entertain more questions. So let's now proceed to the next part of the program, which is the awarding of the certificates to our speakers. So before formally ending the webinar series, may I call on Dr. Drexel Camacho for the awarding of the certificates of appreciation to our speakers and the closing remarks as well. So may I also request Dr. Fekaling Ason, if you're here, and Dr. Mel Garcia, if you're here, to turn on your videos, please. Thank you.
Okay, so join me in thanking Dr. Karen Lacerna, Dr. Rodolfo Sumayaw, Dr. Fe Calinacion, Dr. Mel Garcia. So let me read the certificates that we're going to give to them in appreciation of their sharing of expertise. Okay, so DLSU Central Instrumentation Facility and the DLSU Chemistry Department in partnership with DOST PCHRD and the DOST Balik Scientist Program present this certificate of appreciation to Dr. Rodolfo Sumayo Jr. for sharing his valuable knowledge as guest speaker on trends and approaches in analytical science, the metabolomics approach and its different applications, season 3 on March 19, 2021, with his presentation entitled Metabolomics, Bridging Basic Research and Clinical Medicine, signed by yours truly. So congratulations, Dr. Rodolfo Sumayaw.
Thank you very much for the certificate. Highly appreciated. And thank you for inviting me. This is truly a great honor to be able to give a presentation in this huge audience. And very delighted for this invitation as well. And I'm wishing success to all of you, to the DLSU CIF. What else? I think I cannot thank you enough for this. So kinabahan talaga ako this morning kasi ang laki ng audience. But this is actually a mark of success of this event. And congratulations to all the organizers and to all the speakers. Thank you po. Maraming salamat.
Thank you. And we also like to award the certificate of appreciation to Dr. Emmanuel V. Garcia. Dr. Garcia, are you here?
Yep. Thank you. Thank you so much, Professor Camacho, for having me here. And thanks to Dr. Karen Lacerna. I look forward to working with you. There's a lot of ideas already. And it seems like we can do it already now that you're there.
Yes.
Maraming salamat po at saka sa lahat ng mga nagtiis ng isang linggo.
Okay, thank you, Dr. Garcia. And also would like to award the certificate of appreciation to Dr. Maria Fe Calinacion. Thank you, ma'am, for sharing your expertise with us.
Maraming salamat din po, Sir Drexel, and to all of the staff from the Central Instrumentation Facility of DLSU. Thank you for this opportunity to share our experiences in the different applications of metabolomics. So I really appreciate the crowd, very interactive crowd from the past 3 sessions. So we're looking forward to future collaborations with everyone.
Yes.
Thank you.
And also, we would like to award the certificate of appreciation to our keynote speaker who presented her um, lecture for the last 3 weeks. And thank you, Dr. Ana Karen Lacerna.
Maraming salamat din po, Sir Drexel, and to the whole DLSU CIF team for getting this webinar in rolling. So, kumbaga, it was really a great privilege and honor to be able to share yung mga learnings ko previously. And also, again, much thanks to to DOST, PCHRD, and the Balik Scientist Program for this opportunity. Maraming salamat din po for all participants, to all the speakers. Maraming salamat po. I enjoyed really having this webinar with you all po.
Okay, thank you. And with that, we would like to close the session. So today ends the 3-day webinar series we held for the last 3 weeks. Please join me in thanking our speakers by putting in like, thumbs up, and clap emojis on Zoom and in Facebook Live. Thank you so much, Dr. Ana Karen Lacerna, for sharing your expertise in metabolomics, teaching us about the what, the how, and the chemometrics in metabolomics research. Thank you also, Dr. Maria Fe Kalingacion, for sharing to us your research journey in rice metabolomics. Thank you, Dr. Emmanuel Garcia, for sharing your endeavors not only in coffee metabolomics, but also in the whole coffee chain. Thank you, Dr. Sumaya, for your talk on the clinical applications of metabolomics. So indeed, we are grateful for the new knowledge that we gained from all of our speakers. Now, it is our hope through this webinar series that we were able to ignite some passion in our participants to do actual research. So metabolomics is a very powerful research area, and it can be more interesting if you are involved in it. And as you can see, it is highly technical. So that means that you need to have advanced training because it talks about a lot of technical aspect. So for our participants here who are high school students, we advise you to take a BS Chemistry or to proceed to STEM courses in college. If you are a science college student attending here now, you can proceed to take up MS and PhD degrees. You can enroll at the DLSU Chemistry Department for your MS Chemistry and PhD Chemistry degrees. If you are a career scientist joining us here for the last 3 weeks, you can partner with us starting from your proposal planning towards the completion of the project. We can help you on the technical aspect, especially on the instrumentation part, and we can match you with the appropriate professor who can help you on the research. Okay, so we welcome researchers at CIF to hold residency with us, so you can finish your degrees or projects. So please feel free to contact us and help, and let us build partnership as we explore together more research endeavors in the Philippines. Again, thank you so much for joining us for the last 3 weeks. Please look forward for more announcements for another series of semi-webinars that we will be presenting for the coming months. And we look forward again for real interaction with you through actual research. Again, maraming salamat and God bless us all. And please keep safe always. Thank you.
And thank you very much, Dr. Camacho, for closing
Thank you
remarks.
very much.
Ingat,
Have a
ingat.
nice day and keep safe.
Sir, ano po, ito po muna tayo saglit. Before we end, we would like to request you to turn on your cameras for the last time for a Zoom fee. Ayan. So, document lang natin yung event through a screenshot. So, last na po ito, wag na kayong mahiya. Ayan. Open nyo na po yung mga cameras nyo. So, ipopost po natin ito later doon sa ating CIF Facebook page. So, okay. Are we good? Ayan. So, CIF team, okay na tayo. So, let's start. For the first screenshot, we have 5. Medyo marami today. So, again, counting 1, 2, 3. Second screenshot. Okay. 1, 2, and 3. Third screenshot. 1, 2, and 3. Fourth screenshot. 1, 2, and 3. And then fifth screenshot. 1, 2, and 3. All right. Hopefully, already captured everyone. So ayun, thank you so much for attending. From all of us here in the DLSU CIF, we hope you all enjoy the webinar series. And we look forward to seeing you again in our upcoming webinars for this year. We have a couple lined up. We thank all of you for making this webinar series a fruitful and a successful one. Please follow the DLSU Central Instrumentation Facility Facebook page for updates and future webinar schedules. Take care and continue to stay safe and healthy. Goodbye, everyone.
Thank you. Congrats, congrats.
Bye.
Bye-bye.
Have a nice weekend po, everyone.